like you could think that they build nice little dams for themselves, and maybe they do, but they actually have a huge role in ecosystems, like in natural ecosystems, because dams slow down the river, they prevent erosion. They also tend to flood the surrounding area, which is something that people that want to build houses really hate. Kind of like developers hate the distros. Like you can see the metaphor works. But for like the beavers create an environment in which other species of mammals, amphibs like frogs and all that stuff, they really thrive in those wetlands. And the wetlands also stop wildfires, so they make everything easy to live in, and they help the ecosystem ultimately. Like by slowing down things, they help. And this is what ideally you want a distro to use. Of course, you can use Arch Linux if you want. Like I'm not talking bad about rolling release distros, but if you are developing, maybe you want something slower that you have more control on. And that means basically using stable kernels. And there are two approaches. One is just to have upstream long-term stable kernels, or another very different approach to having a stable kernel is what goes on in CentOS Stream. There are more similarities between the two, as we will see shortly, but they are also very different in how they work. Like, for example, between RHEL 9.5, which is what is used in CentOS Stream, it's basically the same as the RHEL kernel. It has had, in 2.5 years, about 100,000 commits on top of what was 5.14. Doesn't look like 5.14 a lot anymore. It's like 40% of what went upstream also went into the CentOS Stream kernel, but it's still called 5.14. By comparison, 5.15 right now has about 15,000, and an end-of-life kernel like 4.14 had 25,000 over the whole life. Now, RHEL is also going to slow down pretty soon, but still you can see that it's like an order of magnitude almost difference. Why is this? Because it's what we affectionately call a Franken kernel, because it's built from very different pieces, like all put together. So it started indeed as 5.14 back in a couple years ago. But then if you look at RHEL 9.0, there was already some things added from more recent kernels. Some subsystems, they didn't really care about it. Others, for example, networking or XFS, backported little things here and there from 5.16. And if you look at what is going on now, almost all the subsystems have something resembling 6.9 code in them. Some of them are a little behind. Some of them are a lot behind. Some of them that are more sensitive to what Red Hat customers might not appreciate, they just got bug fixes, and they are still at 5.14 level. And in some cases, we really go beyond what is the target release for a given RHEL minor release. KVM, for example, has SMP support, which was backported from 6.11. So not everything in 6.11, but something. So you can see that it is a very monstrous thing. Like, don't try this at home, but it works. Like you can like it or not, but if you have the money to do it, you can do it, and there are some advantages. So what goes into this kernel? Bunch of bug fixes, a bunch of feature backports, and a bunch of really mass backports that update the whole subsystem to a new kernel release. They have like different sizes. Bug fixes can be just one commit, and mass backports can have hundreds. What's this? Okay. But in the end, despite this difference, it's not very different from what goes on in the stable kernels. Because usually, the difference is that with stable kernels, as you develop your program, your software, maybe for 2 or 3 years, you just update to new kernel versions. Once you want to do maintenance, you stick to a LTS kernel, and you just update the LTS kernel. Instead, in CentOS, you will have 5 years of full support, but the first 3 years are a lot faster than the next two. Like after 9.6, as I said, things will slow down a lot. And then there's 5 years of maintenance, where the binaries are available to Red Hat customers to RHEL, but the source is there. Like the source is still available in GitLab if you want. So they provide a very similar product development cycle. The difference is just that with the stable kernels from upstream, you don't really have a choice. Like it's everything in a release and you get it. While every 2 or 3 months. While with the CentOS kernels, like it's developed with 6 months sort of cadence that alternates between the mass backport phase and the stabilization phase. Why would you do that? There is some more guarantees of stability. For every patch and backport that goes into the CentOS stream kernel, there's at least 3 people. One of them is the guy that did the backport, but 2 more that took a look at least at the list of the patches. There are CI bots that look at all the upstream fixes tags, guarantee that those are either included or waived. If something is deviating from upstream for whatever reason, the people there that approve the merge request check it by hand. There is quality testing done for each merge request, at least some kind of sanity smoke testing, but often more. And the sources are available on GitLab, and also the packages can be downloaded through DNF if you are on a CentOS stream release, or on Koji if you just want to see what it's like. So it's a completely different model from the upstream kernel. This is made possible by good upstream practices like having commit messages, having well-defined boundaries between maintainers, and having topic branches so that we can see what was going on and see the way that merges went into the various, merge commits appeared in the various trees. So this would not be possible if it was not for how Linux is developed. Like it's not, it's a lot of work, but it's work that is possible because Linux upstream is doing good things. And downstream, we have a lot more planning. We have a lot more infrastructure with like CI. This CI is also applied upstream, like the continuous kernel integration system from kernelci.org. There's also bots that do all the checks. And we use different tools. You may agree or disagree on doing development by email. But personally, I think that doing development by email is also part of what ensures that we have commit messages, well-defined maintainer boundaries, and good use of topic branches. And downstream, instead of doing on GitLab, and to be honest, I don't think it would be possible to do that thing with email. So to each its own, like different things have different tools. So we have, for example, these CentOS TDX packages that start from the CentOS stream kernel. They add the TDX patches on top. It's maintained by me, Camilla, and also Cole Robinson did some work in the past. And it has some recent, currently is about 1 year old, but that's because a lot of changes went in and it made it really hard to rebase everything. So we are still on slightly older patches for TDX support. But we also include the common code. So those patches are rebased on top of 6.11. They use all the upstream GasMemFD infrastructure, for example. We have the same advantages, sort of, that I talked about earlier with the CentOS stream Franken kernel, where you can have some kind of review of what's going in. It's done on a smaller target. It's done on a moving target. And the good thing is also that it's very integrated with the rest of the distribution. It grows together, and it helps testing what will be in the next release of RHEL. And it's pretty stable and easy to use for development. Generally, again, we stay faithful to the mailing list postings. We just rebase to whatever we got from the Franken kernel upstream. And of course, because it's all integrated between kernel, QEMU, and libvirt, we try to have a consistent API in the BI. Sometimes we have localized hacks so that you don't have to update kernel and QEMU in lockstep, but those are all in the GitLab sources and available kept separate so that you can look at what is done to ensure this interoperability, and we can always remove later when they're not needed. The packages are on a different instance of Koji called the community build system, which is specific for the CentOS 6. very quickly, if you look at how many patches were added, you can see that sometimes there are some bumps, and it looks like the upstreaming effort is stalled because you see it's like gone down in the beginning, but not much in the end. But actually, if you look at it better, you can see that this blue line is the non-upstream patches, and it did go down a bit slowly, but it did. And some of the growth instead is done because we are including already what will be in REL like 1 or 2 months from now, basically. So it's going down slowly, but it is going down. And I think we will cross 200 very soon, like will be 180 patches, sort of, very soon. So in that case, we added the REL 9.4 KVM backport. And here it's when we rebase and the backport was merged. You can see that the number of patches that are upstream patches included in this kernel, it went down a lot because this moved from the CentOS TDX kernel to the actual CentOS kernel. So why is this helpful also for upstream and not just for developers of things like Kata containers? Basically because we try to have a minimal set of downstream patches. We try to limit to what is being actively discussed upstream. And we identify anything that is required, but at the same time, it's not being posted upstream. Like we start from the vendor kernels, we trim it down, and sometimes some things come up and you say, what is this thing? We analyze it, we check if it's upstream, and maybe it was forgotten. We talk to Intel, or we just post the patches upstream. Sometimes we redo the patches in a better way. It's like I said before that curating the set of patches is a lot of work, but it's beneficial not just for CentOS users, also for upstream development. And again, as I said before, for people that work on Kata containers, there's one source for kernel, QEMU, and libvirt that can work together and that you can use to develop. Don't really have time for questions, but I think it's best if I leave it to Fabiano now for the next talk, and then we can have questions together at the end. Yeah.
Here, like we have a small problem with putting this in the presentation mode. Otherwise, half of the slides are going to be just cut. See, like that is like a little bit cut there. Yeah, so yeah, let's just do this, and we are cutting one of the nicest pictures that we have. F11. It's his laptop. I'm not going to do this. Just go F11 for full screen. Yeah, that's good enough. Thanks. Do you go for the slides then? Is this okay? Okay. So first thing to say, like I'm very happy to be here. I'm very happy to be taking over the second part straight from Paulo. I am Fabiano Fidencio. I work for Intel. And together here with me, I have Mikko Ilinen, who has been my right arm inside Intel, mainly now. as you can see, like my right arm, my left eye, you know, like, and we will be talking about like what is on the application side, what we are doing, how we are consuming, what Paulo is doing, and well, a little bit of problems that we faced there. Anyways, just get back a little bit. So the title of the presentation is like living in stilt houses. Stilt houses, for those who are not familiar, we call these palafitas. Those are houses built, you know, across the river banks, and they have to support like high flow, the high stream flow, or the low stream flow. So they have to be prepared for any kind of environment changes there. So those are quite common in Amazon in Brazil. And I just would like to give a shout out to the photographer of this, who is one of the best nature photographers in Brazil, who just gave us the license to just use those pictures here. So that's the analogy we're going to do, because the applications have to just like get around with all the changes that are happening like below them. So this is going to be like more a conversation than a presentation. Do not expect anything too technical. Like, we are just gonna talk a little bit about what like Paulo is doing and other kernel developers are doing, how it's gonna impact the apps. Just use the space button. Yeah, and then we don't have a PDF something here, so yeah, happens. Oh, it does work. Yeah, so we're gonna go through the known challenges, and next slide, just gonna talk a little bit about the known challenges. We're gonna go a little bit about the workarounds that the distros usually take doing this kind of development, and also the drawbacks that this is gonna just bring. So yeah, let's. And one like quite important thing that is like, what are the expectations that we have, maybe naive expectations that we have from hardware vendors. How we can get some help from the distros, and the naive expectations that we have from the hardware vendors. So Paulo mentioned a lot of things here, and one of those that you you can clearly see, like, there is a high flow of changes coming. In the early stages of development, those changes are usually incompatible, right? Like, usually people are doing this development, they are not getting things right on the first time. So applications, usually like hardware vendors want to test this kernel code together with the applications they are developing, and that end up like putting us in a situation where we have to deal with incompatible changes and have to deal with these in the application layer, which is just like a mess. Then, because of that, we end up like having to support different kernel stacks. So let's say I have a hardware that I want to enable a feature today. I will start developing on top of 6.11, maybe 6.12 when it's released. All the patches will go upstream. There is a review coming, and then like by the moment I can resubmit something, it's like 6.15, maybe 6.16. And then like we will get the parts that we have done right and pretty much rewrite the other parts. And for the applications that have to support the other part, you end up like just with those broken changes that you have to just like have your workarounds there. And as Paulo mentioned, like when you bump a version of the kernel, there is a lot of features that just come for free, a lot of bug fixes that will come for free, and a lot of bugs that will also come for free, right? This is the nature of what we do. And maybe it's okay to have like a big team to deal with that. Usually people don't, right? So, and the last part is, when you are dealing with the first versions of the stack, you are actually relying on something that will never see the light of upstream, which is not good to anyone. And then like we have the known challenges that we are quite familiar. Hardware development is slow compared to software. Software development for this part of confidential computing is quite complex, as Paulo could mention here. Then software enablement can and will take years. Like SGX from Intel is one example. But even if you take a look at the line that timeline that Paulo shared about the S&P and TDX, this is taking like 7 years, right? That's like a lot of time. And of course, the amount of moving pieces is huge. Paulo mentioned about kernel, QEMU, libvirt. There is also like OVMF, the firmware that is involved. And then when you get to kata containers, there are other components that are involved that are related to attestation. So kata containers itself is moving, confidential containers itself is moving. So there is like a lot of moving pieces that we have to just put together. So what the distros usually do is something that Paulo mentioned already, is like, hey, we are gonna just do the development on top of one specific version, put the source code somewhere, maybe sometimes a link, not even a GitHub, where someone can just go there, download that, build it. Maybe it will work, maybe not, hopefully it will. Hopefully they will get all the parts correct that will make it work. But that's painful. That's like really, really painful. And there is also something else that is complicated, that is usually like when you start shipping this to customers, right? Because you have your hardware out there, you want the customers to start trying this. So you start just shipping those links to customers and say like, hey, have fun with this. And then your customers may end up building something on top of something that will never, ever work, or will work on that specific tree only. That causes a lot of like, problems to handle integration, problems to handle maintenance, which is fine for, let's say, Amazon, Google, Meta, Alibaba. They have huge teams. Middle-sized companies, not so much. So that becomes a problem. And we mentioned about maintenance, right? So maintenance nightmare. We are just going to start talking about the drawbacks now. Next slide, please. Yeah. Drawbacks. Maintenance nightmare is the main drawback that I can see here, like, because I can just imagine like one small company having to go through the whole process that Paulo mentioned about curating patches and testing and like everything. But there are also other problems, like building your own stack is not easy. Who here is building their own kernel? Pretty much everyone, right? But this is the wrong audience, right? The customers are not building their own kernel. They don't want to spend time on that. They don't want to have a way to, put this whole thing together. They want to rely on someone that does that for them. And usually they are paying someone to do that for them already. And then when you are building your own kernel, you get into some kind of lack of contractual support, which is like, let me ask you a question here, for instance. We have some folks from Red Hat. Does Red Hat support running your own kernel? Of course not. Mostly not, right? So if you want to do any kind of reasonable experiment, like that everything is going to be supported, ideally we should have come something from the distros, right? From the enterprise ones, either coming from SUSE, from Canonical, from Red Hat. So this is one of the points. And then there is like, those two go together, a lack of communication, usually coming from the hardware vendors, and a problem with the expectation coming from those consuming the content from the hardware vendors, right? The hardware vendor is not gonna put something upstream and tell you, well, it's gonna change a lot. I'm not sure if you should use, right? The hardware vendors are just there saying like, my hardware is amazing, use it, get it to production as soon as possible. And then the customers are just like, oh, whoa, we have some like a reasonable assurance of maintenance there, which is not the case, which is really not the case. So here we come to the interesting part. We need the beavers, right? We need to get some help from the distros. And distros can help us a lot on this. The first thing is, And I hope, like, do we have folks from hardware vendor here? Do we have folks from AMD? Do we have folks from ARM, RISC-V, maybe? Well, we have at least one, okay. I know that, like, the most part of the folks working here, they work for distros as well, right? So I may be just praying to the choir here, but distros maintainers know way better what are the distro specifics. They know way better what are the timelines they are comfortable to get the patches in. They know way better what is acceptable for them to maintain something. You know, maybe for 4, 5, 10 years if needed. So, and they know exactly how they are going to do that. What are the criteria for everything? So the distros maintainers are here to help, and they know better than the hardware vendors about what has to be there and how things have to be there. And this usually happens because the distros maintainers, well, I can surely say that in our case, the folks that we are dealing with, we are like working together with folks from Red Hat, folks from Canonical, folks from SUSE. They are kernel maintainers. They are QEMU maintainers. So they are following closely what's happening upstream. And if you are maintaining a project downstream, you should be following what's happening upstream as well. So by the moment we get to agree that distro is going to do like a better work for us than just like a link in the internet, we can see like, I think like it's quite easy to agree that installing something from the distro with your DNF install is way easier than building your own stack. DNF install QEMU KVM, and then it's going to bring the firmware, host kernel. So you have everything that you need there already. And there is another important part that is how this easy installable and implementable path allows us, like on the application side, to just start working on the products that are built atop of the distro. If it's not clear for everyone what I'm talking about, let's think about OpenShift. OpenShift is a product from Red Hat. It's built atop of RHEL. They do a rebuild of RHEL. It's called RHEL CoreOS. And it's not so easy to get a bunch of binaries here and there and just like layer this atop of what OpenShift is using. But thanks to the work done on CentOS String, it's very, very easy for me to just have like an RPM layered atop of what is OpenShift providing. And of course, I should not distribute this to a customer. But this allows me to start testing and integrating that kata containers or confidential containers works very well with OpenShift and TDX today, and it does, before everything gets upstream. So whenever things will get ready, those things will get ready together. And that helps us a lot. And for the distros, it's fine. It's very, very fine if something comes as a third-party repo. We are not asking the distros to just like, hey, we have this patch here. It may not be stable. Support this for 10 years. Right? This is insane. We are not asking for that. But just try to give us an easy way to test it, integrate it with your distro. We really want to make sure that the QEMU that we are running is going to be compatible with everything else that you have in your distro and things like that. Let me just pass the mic to Miko.
Okay, yeah, so I'm going to walk through this one slide. I apologize my voice. It won't take long. So what would be our expectations from the hardware vendors, or best practices rather? This is something that is based on what we have seen. Take of these as lessons learned or tips to avoid any road bumps in the future. One thing related to what Fabian said just previously on this distro integration. Packaging is a pain. Distros and distributions know how to do it better. This is based on some of our experiences when trying to get some of our attestation-related packages integrated into the distributions. We have seen or faced some struggles getting our existing packaging to meet the quality criteria for packaging that the distros may have. They are often much stricter criteria and what we had learned was that, okay, we did something, but hey, that didn't quite meet what the distributions were expecting. So get the integration work started early on, get help from the distributions. One good example where this has been pretty successful, we have had Daniel helping with some of the attestation-specific libraries on getting the reproducible builds support improved. Reproducible builds is a critical, at least for the libraries that we are dealing with here, related to the attestation and quote signing. One other thing that's also critical or important to remember on this packaging side is if you have your software that comes with new releases in the future. So make sure you know what the distribution integration timelines are so that you get to deliver the best and the latest features to your customers also for consumption. And the second thing, which I think is the most important thing or the most important takeaway out of this slide is the collaboration with competition can be very beneficial, and there are lots of examples here that we could highlight. I have two examples covered here. So first is the recent addition in the Linux kernel to get a vendor agnostic confidential computing report API agreed, which is something that is now we are able to get rid of all the vendor specific IOCTLs. We have a common framework that we now know how hardware vendors get their TEE support integrated into the guest kernels. On the Cocoa side, we already have TDX, and most recently, if I remember correctly, also ARM moving to use this interface. I think we have still AMD support missing, so we welcome any contributions to get that part also covered. Community engagement, so get that going sooner than later. Cocoa side, it's a great example where the project got started. So it was taken as one of the main drivers or main goals for the project that it needs to be vendor agnostic completely. We support, I think, like 5 to 10 different hardware TEEs, but it's done in a way that none of these hardware specifics are visible to any of the users of Cocoa, which I think is pretty amazing what we have to offer. So it's all hidden under the hood, and no one would know if you run on TDX or SCV. So that's pretty cool.
Yeah, this is like, we have like 5 minutes, and I think that's one thing we can just take questions, comments. Paulo is here, so we can take questions for the previous session as well. So yeah, your time.
So a couple of comments on the previous slide. The first thing here is, I think, at least from the hardware vendor perspective, we are starting to collaborate quite a bit earlier. Paulo is aware of what we're doing in the trusted IO space. But at the same time, one of the things you have to keep in mind is, at least when we try to unify interfaces, first vendor in gets to make their choice. The second vendor in gets to unify. So, well, we are all trying to get features enabled quickly.
So it depends. Like the first vendor certainly has more flexibility, but sometimes it's not feasible to have a different user space API, which is what I mentioned very quickly. In like SMP code has been ready for a while, but we were stuck on GasMMFD because there was an understanding that GasMMFD was an important part of the enablement of confidential computing. So I did feel bad for AMD that had the code almost ready, but the first vendor has more flexibility, but they should still do it right.
Yes.
I would say, like, regardless of who is the first vendor, like having in mind that we may have a common architecture is something that they should always be prepared for. So you have more freedom, but you also have more responsibility on what you are doing, right? So, exactly.
Come here, Dhaval. Come here. We are going to chat a lot. Come here.
We don't have much time, so let's...
All right. So,
I'm trying to bring my context back in. So, at least with Trusted IO, for example, we are trying to have all of these discussions early, but sometimes it's pretty hard to try to get to a common interface without seeing what's happening elsewhere. Last year, when we started Trusted IO, IBM folks had their own implementation where we did not think we needed Linux support, for example. Now we're finding out, well, maybe they have similar abstractions. These things take time.
This takes time, and this is a valid approach. But if you have the opportunity to talk to someone while you're doing this, do the talk. This is the main point.
generally, what ends up happening is the talk happens upstream, and people don't know someone else is also working on it. So it's good to post patches early and often, and maybe there's an opportunity to just push things into staging instead of having to. And that's a way to enable collaboration before figuring out what the user space APIs are going to be like.
Yeah, there are rules for what goes into staging, but we were discussing about having our own Linux Next tree that includes both Intel, AMD, and hopefully also ARM and IBM technologies. But with a small catch compared to Linux Next, that is, if you have conflicts, Linux Next tries to merge things, we would merge neither. So you have to collaborate if you want the tree to be available to users and to distros in the same way. Yeah. And also include both kernel, QEMU, and libvirt in the same GitLab organization. Like
so it's
firmware 2, yes.
So it's a CentOS SIG.
No, it's an upstream thing that we just talked about and may happen. We don't know when, but it's an idea.
Well, it could be a CentOS SIG. Why not? Because eventually that flows into...
No, this is for upstream. Then if CentOS wants to consume it, that's a different story. But this would be for upstream developers, like both them and the Linux kernel.
I think the more important thing over there is the user space API anyway.
Yeah. Yeah, so we need to include QEMU so that you can have something that works at any moment. But of course, the user space API is subject to change, and you would have to have everything in lockstep.
Exactly. Yes. Exactly. So one of the things about the distro aspect of things also is that the hardware vendors probably do not know how to do packaging right. There are a few people who would, like you mentioned, Paolo, Daniel probably. So having shell scripts from distro vendors already helps. From the hardware vendors helps people who know how to do packaging right, and they can convert shell scripts into RPM or whatever else format.
Yeah, that helps, but like, let me just make my point like a little bit more clear here. One thing that we have noticed is like people inside hardware vendors, companies, they are very, very opinionated on their capacity to do packaging better than, let's say, a company that is like 30 years out there doing packaging, right? And they are like, oh, packaging is easy. Well, It's not, right? We have like a lot of companies that their own business is make sure that the packaging is sane so you can use it without any kind of problems. So having a script will help, but like knowing the limitations of your team and getting to the distros or someone from the distro and say like, I need help to package this. How do you think this should be packaged? Is the most important part.
And also on the other side, like I can and will gladly pick up the final stages of a series so that I can integrate it with things that I know that are going on. And especially when you need to do very fast turnaround to fix the last couple of things before merging a series. But at the same time, for the first part of the work, someone like me needs Intel because I don't even have the hardware. Like, how do I do development?
Same
So
goes for
it
me.
has to be a multi-step process with different people working on each step.
Yeah, same goes. So, which is kind of why I said CentOS SIG also makes sense in that upstream world, because just having a SIG at the outset helps with the entire view.
I agree with that, but like that's a second stage. The first stage is like let's have everything upstream, and then
Of
like we
course,
get into
yeah.
the SIG. I would suggest like just one thing. If someone can work for the distros companies for like maybe almost 10 years and then move to hardware company, they can start like forcing that, right? So I'm not saying that someone here has done this, but well.
Exactly 10 years at Red Hat and now at AMD. So.
So I wanted to mention one sort of specific example of something that we ran into in confidential containers, and also put a slightly different spin on things. So one thing that we rely on for attestation for S&P is the extended report. We assume that when you get to the verifier, you're going to have the extended attestation report, and that's how we get like the VCheck or the VLAC, right? So there's a little bit of a history to that feature in QEMU, and the kernel, originally the extended report was set like via an ioctl, and it was set per like host, and you would set it like once per boot, and then you would just get it whenever you did an attestation inside the guest. And then at some point it was decided upstream that actually QEMU should have it be able to be set each time, like for each guest, which is pretty reasonable. And then there was a decision upstream pretty recently, I think, to actually not include this at all in QEMU or the kernel. So now we don't have that at all. And there is a fallback to this. You can get this from the verifier side, although it's not totally optimal. But this is a very concrete example of how we need this thing to be able to do attestation. We write some code that depends on it, and it changes. And we can't really complain about that because we're dealing with upstream stuff. But also, the longer it takes these lower levels of the stack to merge something, the more that higher levels of the stack are going to be doing stuff like this, and that's sort of inevitable. But
yeah, so talking specifically about the attestation report and the extended report, that is actually something that was dropped just because it was not ready, to avoid delaying even more the core support. But another example that I would make that hasn't even been posted upstream yet is the VMPL and SVSM support. So these are things that you will get from a vendor kernel, you will not yet get from upstream, but something like the CentOS SIG could actually include it. And like now I've done my first part of the job, SMP is included. I want to already move ahead and include this VSM support, even if the API is not finalized.
Yes, so I think one difference between those features is that this was included and then removed or changed, and that's a little bit annoying. But I actually am not that upset about this, because I think that this is kind of, in some ways, the point of confidential containers. Yeah. Like Miko was saying, this is a project that's trying to unify these things. This is the work we're doing. Like, this is what we give users, is that we take the bullet here, in some ways, almost like a distro would, to get all these things to work seamlessly.
Yeah, there is some similarity between what developers like Kata containers do and what the distros do, and that's why collaboration works well. Like, time is over.
One last thing that I would like to just show here, like there is this last slide that I would like to leave you guys with, that is, a software product is not fully developed unless it can be easily and widely used. And usually it comes by being present in enterprise distros, right? This is something that people buying the content to use, they want to have this box to check that if something goes wrong, we have the enterprise on our back to just cover us on that. So when you are doing a product, you made the hardware, your product's not done. You made the software, you put this on your hardware vendor web page. This is not done, right? It's done when people can actually use anywhere in an easy way. And that's it. Thanks. Thanks for being here.
Uh, Hello, everyone. I am Mominul and my colleague Zinan. We work for Microsoft in a small team called Linux Systems Group. I'll be co-presenting with my colleague about the CVM performance on QEMU, KVM, and Linux root partition for Microsoft Hyper-V using Cloud Hypervisor as the VMM. So when we talk about Microsoft, everyone is a little bit interested what Microsoft doing in Linux and open source. We are heavily into Linux and open source, and the stack we have been working on recently. I will be presenting in this slide what are the virtualization stack that. So in this diagram, you can see the traditional Microsoft Hyper-V. It works on top of hardware, and we have the root partition as the Windows. As you know, like the type 1 Hyper-V, like JN, hypervisor, you usually have the host partition, and this has been the Windows for a long time for us. And our team, Linux Systems Group, we have been working on an alternative operating system where we brought up Linux as the root partition for Microsoft Hyper-V. So the purpose of this stack is, like, a lot of customers, they will be interested in using Hyper-V, and also they want to get benefit from open source Linux-based operating system. So that's why we want to combine the power of Linux and Microsoft Hyper-V, where we can cater to the need of Linux native customers who need the virtualization stack. And this could be as an alternative of KVM QEMU Vert stack. So let's zoom into the Linux root partition we have with the Microsoft Hyper-V. So we have the hardware and the Microsoft hypervisor, and we have the Linux root partition. In Linux root partition, we have a kernel module. It's a dev MSSB. You can say it's some kind of similar to dev KVM. And this module exposes some of the IOCTLs to, like, manage and create the virtual machines on Microsoft hypervisor. And this driver, we have some patches already upstreamed in the Linux source tree, and also some of our patches are in pending review. So it would be great if you folks could review and give us feedback. For the virtual machine monitor, we are using Cloud Hypervisor. You know, like it's a lightweight and Rust-based VMM utilizing the Rust VMM crates. And Cloud Hypervisor is also a member of Linux Foundations. So Cloud Hypervisor has KVM support. We, as a Microsoft, we added the support for Microsoft Hypervisor to launch guest. Cloud Hypervisor supports both Linux and Windows as the child partition. This slide actually compares the stack on the confidential VMs on KVM QEMU versus Microsoft Hyper-V and Cloud Hypervisor. So you can see on the left side, the firmware is used OVM or UEFI, and in our stack we are using a new file format that made by Microsoft. It's called IGVM, Independent Guest Virtual Machine. So in the confidential VMs, we have the AMD hardware on top of that QEMU KVM, and on the right side we have the the difference is like how we launch the VM. In the case of KVM and QEMU, we use the OVMF, and we on the right side for the Microsoft Hyper-V, we use IGVM. So IGVM is a blob file that is generated by a Python script that is already been open sourced, and the script has a Linux loader that can embed Linux kernel, initrd, and that script can generate VMSA page on the fly and put it into a single IGVM file, which will be later used to load the guest with the specified memory contents from the IGVM file. So for the rest of the talks, when I say CVM, I meant to say confidential VMs on SaveSNP with AMD SaveSNP. But we know AMD, the other vendors like Intel TDX and ARM CCA, they also support confidential VMs. Let's try to describe more into the what is IGVM file that we are trying to use. You can say it's a vert stack agnostic way to package the launch information for a guest and into a single file. And this file is, you can say it's some kind of ELF or PE for VM launch. The file has some ordered list of directives with accompanying data specifying how the vert stack should load the guest. And there are two open source crates that we use for parts and generate the IGVM file, and that is part of the Rust VMM repository crates.io. So while we added support the CVM in Cloud Hypervisor, we had to make a lot of changes. I want to go into a little bit into that. So in Cloud Hypervisor, just to mention, we are supporting nested CVM in Cloud Hypervisor. So we have added support for IGVM parser in the Cloud Hypervisor. That is built on top of the open source crates that I mentioned in the last slide. We parse the IGVM file and load all the guest launch information into the guest memory. We do some SEV, SNP specific operations like handling CPU ID, secret pages, and many more. We had to change the vCPU run method because that is mostly based on KVM and also non-CVM version of that in the Cloud Hypervisor. So we did some vCPU run method and handling all the GSCV and guest hypervisor communication block. We have there is a support in registering doorbell and GSCV page in the Microsoft Hyper-V. And some other supports like MMI, we do a lot of MMI exits from the hypervisor and some IO and some debug and etc. There is an interesting piece of code base that we had to change in the Cloud Hypervisor. Those VART-IO thread adaptations. In KVM, KVM has its own freedom. It handles most of the things in kernel. But as a type 1 hypervisor, Microsoft Hyper-V, it actually offloads some of the handling in user space. So in the Cloud Hypervisor, there are VART-IO threads when they do IOs, all these VART-IO ring-related guest memory and also software IO TLV, those are restricted pages from the guest. And before doing an IO or accessing the pages, we have to make sure the pages are shared with the VMM. So how do we do? We ask Microsoft Hyper-V to give access the pages, and Hyper-V actually gives the VMM to do IOs, and we are free to go. The problem with this, on the thread level, we don't know which pages are already have access and which are not. In order to solve this problem in the common layer of the Microsoft Hyper-V related abstractions in the Cloud Hypervisor, we do some caching. what are the pages that are already like shared with VMM. So we just maintain a simple bitmap to track that. Then that arises when the guest is revoking the access. So when the guest revoking the access of those pages, we also get a VMG exit, and we like make changes to the caching layer. So next few slides, we measure the performance between the stack KVM and QEMU versus Microsoft Hyper-V on Cloud Hypervisor. So my colleague Zinan will be presenting those performance numbers and more details.
Sure. Let's try to look at the test setup first, right? So in the test setup, we have two different kinds of setup. But for the base setup, we are using AMD 7SP hardware at the bottom. For the L0 hypervisor, since it's a nested setup, we have two different kinds of hypervisor running. For L0, we are using MSHV in both the scenarios, and we run on top of Windows root partition. We have differences in terms of L1 hypervisor. So on the right side, you see KVM. On the left side, you see MSHV. In case of MSHV, we are using Cloud Hypervisor as the VMM inside the Linux root partition, and then we launch a nested CVM guest. But on the KVM side, we do QEMU as the VMM, and then we launch another nested CVM guest. So what we want to measure is the perf difference between these two nested CVM guests, which are launched on two different kinds of word stack, right? Just to do first rounds of experiment, we decided to test the network throughput. If I describe the hardware setup, we have AMD EPYC processors with 1 TB of RAM available in the host. For the L1 VM that was shown in the previous diagram, we have 16 CPUs with 32 gigs of RAM. We do two different sets of experiment, one with single queue and the other one with multi-queue. These are different setups in which what IONet could be run with the turntap interfaces. So in the single queue setup, we have a 1 CPU and 4 gigs of RAM. In the multi-queue setup, we have 8 CPUs and 8 gigs of RAM. So what are we comparing, right? We're comparing 4 different scenarios. The first one being a plain vanilla nested VM, right? It's not 7SP enabled, but just nested L2 guest, which is run on top of Cloud Hypervisor and MSHV. The second one being KVM QEMU with 7SP nested. The last two are very MSHV specific. The one thing is we do with GSCB remapping and without GSCB remapping. So let me explain you what is these two things are, right? What is GSCB remapping in the first place? So GSCB is the guest hypervisor communication protocol on 7SP. Initially, Microsoft Hypervisor did not allow you to access the GSCB page directly in the VMM. In order to access the GSCB page, when you're handling the VMG exits, you would need to do additional sets of hypercall, right? And these hypercalls, for example, you have to update RAX register, you would need to do an hypercall instead of directly accessing that page. Even though it is shared with you, you would need to do an hypercall. This was causing a lot of performance degradation. So we asked the hypervisor team to add support for remapping this page into the VMM process. So basically, MSHV maintains this as an overlay page, and that overlay page is given access to the it allows us to remap that page into the VMM process. In this way, we kind of got rid of the context switch that we needed to do when you have to update the GSCB page before. Now we can directly do read writes, and this helps us improve a lot of performance. So if I go back to the previous slide, right, if you look at the numbers between with and without GSCB remapping, there's a significant difference. But with GSCB remapping, we were able to get closer to the performance of KVM QEMU, which also does not have this problem because they keep the pages mapped and they can directly access the GSCB page. I see that there are some differences in terms of multi-queue setup. I think that is another design choice of MSHV that it allows. So whenever you have to access a shared page that the guest has shared with you, you would need to do another set of hypercall to actually map those pages into the page table of the VMM, because MSHV by default unmaps everything when the pages are made exclusive from user space or the host part. So you would need to do another hypercall. So basically, all your software TLBs needs to be remapped and this causes like the difference because there's an additional hypercall that needs to be performed. The next round of experiments that we did was with the block IO. Similar kind of a setup, again, the same AMD EPYC processor with like the same L1 VM and the L2 VM. But we did like two different kinds of experiment. The sequential read writes versus random read writes on a 4 gig disk size. And what we noticed that we are far off from the non-7 SNP scenario, but we are like as good as like KVM QEMU, or even better at some point, right? Like because of some caching logic that we have built. When it comes to the CPU stress test, we run like a small sysbench, which tries to calculate like our prime numbers. We noticed that like both QEMU, KVM, and MSHV were like comparable in terms of like raw CPU performance. So that concludes our like the performance experiments that we're doing. But we have like some discussion points or like future work that we want to do to improve the performance even further. So one of the things that we have a bit of troublesome is like ACPI tables. ACPI tables usually contains a lot of dynamic information, and if you want the ACPI tables to be part of the attestation report, then you would need to generate ACPI table for each of these dynamic information, right? For example, let's take like CPU count, right, which is usually present in the MADT table, right? And if I have to include the MADT table as part of my attestation report generation, then I need to generate as many IGVM files as many CPUs I want to support. This is really painful. So what we have done as a workaround is like have a PV interface instead, through which guests can be made aware of how many CPUs it has instead of using ACPI tables. But that can also go out of hand, right? Like how many PV interfaces we are going to develop. I think I would like to know like what is KVM QEMU community doing over there, right? Like are they excluding the ACPI tables from the attestation report, or have like a small firmware which takes care of generating the ACPI table, which is measured, right? Like for example, we can think of firmwares like TDShim, which is on Intel TDX, takes care of generating the ACPI table. So we pass like a limited set of ACPI tables to TDShim, and then TDShim takes care of generating the extended ones. Since TDShim is measured, so we can rely on like the TDShim is doing the right job. But TDShim does not support 7SNP. I think there's an open ticket to add support for 7SNP. The advantages of using TDShim over OVMF or UFI is like the binary size. The thing is like the binary sizes of OVMF UFI is like huge. If the binary sizes are huge, it takes a lot of time to boot because all those pages needs to be measured. And what we have observed in our testing is like hashing rate with the PSP is like very slow. It hashes pages at the rate of like 2 milliseconds per page. And if you have like a lot of things to measure, then you will see like a lot of initial time that is taken by the PSP to measure those stuff. There's another thing that we have observed in our stack is like when we try to boot like large guests, it takes up a lot of time. For example, large guests, like it's like 200 gigs of RAM, right? Like if you have in a guest, then it takes up a lot of time. Majorly, as an optimization, what we did was like previously we were using 4K pages for guest, and each 4K page needs to be made exclusive before the guest is being run. So that was taking up a lot of time. So as an optimization, we started using 2 meg pages instead of 4K because I think 1 gig are not supported by 7SNP as of now. So we went on to 2 meg. That improved the performance, but still it takes up a lot of time. It takes around 45 seconds, if I remember correctly, to boot up like a 200 gig guest. We also want to add support for live migration on AMD 7SNP on Cloud Hypervisor. I think this one will require some more coordination from AMD. With that, I'd like to open the floor for Q&A.
In your performance numbers, there was a visible performance gap between SCV enabled and ACV SNP disabled.
Yeah.
What's the cause for that? Is it bounce buffers for I/O?
Yeah, software RTLB, the bounce buffering.
So, like speaking about like guest firmware and OVMF,
Yeah.
is there a chance that we will see a firmware, like an open source OVMF which works well with Hyper-V? Because as a CVM guest owner, I'm interested in getting like predictable measurements, you know?
Yeah.
So I need like a reproducible build or even an option to bring my own like
Yeah, I think
firmware.
with IGVM, we are trying to solve that problem, right? Like if you can build your own IGVM file. So right now we are not doing any sort of firmware. We are doing a direct kernel boot with IGVM actually. So you can build your own IGVM file and you can bring that IGVM file to Azure and like use that.
Right, but what do I put in the IGVM file?
You use your kernel, your initrd or whatever you want to put, right? Like it's a small Python script. It takes your kernel and initrd and
But like on the firmware level, like I will still need to put like OVMF binaries there, right?
No, you don't need. We're doing a direct kernel boot.
You're doing direct kernel boot.
Yeah.
Okay. Yeah.
Regarding the ACPI tables and measuring those, I mean, it seems like IGVM would be a good place to consider placing that information. Has that something that's been looked into?
Yeah, so currently we are putting the ACPI tables into IGVM file, but the problem is IGVM file is generated before the guest is booted. So you need to, so for example, right, if I want to launch a guest with 4 vCPUs, I need to tell the IGVM file as well at the time of generation that I want to launch it with 4 CPUs so that it can generate the correct set of ACPI tables. But the problem with that is like now we have too many IGVM files, right? Like too many IGVM files to handle around and too many measurement files to keep take care of and all this kind of
So
stuff.
it doesn't scale.
It doesn't
very
scale.
well. Okay.
Do you have any plans to try this on ARM or other hardware architectures?
Yeah, that's a work in progress. Since we kind of have an internal version for KVM, which works with IGVM files, but we haven't tried it on ARM yet. Like CCA is still work in progress on ARM, right? So we don't have hardware to test it out.
Hi, Janank. What is the plan for the dev MSHV interface? Are you still trying to get that upstreamed? And who else would be interested in using that, especially since there are Hyper-V enlightenments in normal Linux KVM?
Yeah, we're still planning to upstream the dev MSHV part. The enlightenments are only for the guest part, right? Like if you actually want to use the hypervisor, right, the capabilities of the Microsoft hypervisor, you would still need our driver to have a layer where you can natively use the Microsoft hypervisor and launch guest on top of it without using the Windows, without getting the burden of the Windows ecosystem. That is like the use case that we have, right? Like for example, like Kata containers, right? Like where we are using it is like as part of our confidential containers. We're using like Kata confidential containers, which is running on top of this stack. And that helps us out there, right? Like so that we don't have to integrate with the Windows ecosystem, which also has a parallel solution called ACI, the Azure confidential containers. But yeah, this is like a more Linux native thing. The patches are still work in progress. We got some feedback from Greg and the folks out there.
Yeah, I saw that, like a 5,000 line commit to add a driver. Yeah, difficult to review.
Difficult to review. We're trying to reiterate over it. Yeah. Thank you.
All right, good morning, everyone. My name is Tom Lindacki. I work at AMD on the Linux kernel team, focusing mainly on confidential computing technologies. And today I'm going to talk to you about VM privilege level feature of SMP and how we are going to use that to create levels and execute within those levels and why we would want to do that. All right, as a first thing I'm going to do a review. I'm going to go through the SEV review pretty quickly. Hopefully most of the folks know a lot about that already. And then I'll focus a little bit more on VMPLs and the Secure VM Service Module, or SVSM. And then we'll get into exploring some options on how we can create these VMPL levels and how we can switch between them. SEV, and Paulo talked about this a little bit this morning already. So it's a way of having a guest protect itself from the hypervisor and from other VMs on the system through cryptographic means. So every guest gets a unique ASID, or address space identifier, which gives them then a unique encryption key, and we encrypt the memory in that key. SEVES is the next step in that, and that's where we encrypt the guest register state so that the hypervisor can't see the register state as the guest is executing. We split out the save area, which used to be part of the VMCB itself. In order to do this, that save area is encrypted. Every time we do a VM run, we decrypt it, load that guest state into the guest, and on VM exit we save that back into the save area. That does present problems if you're trying to have the hypervisor do certain things for you. Paulo mentioned like an MSR read. CPU ID is another thing. We use an unencrypted page or a shared page in a standard where we can communicate state to the hypervisor and get the answers back, and that's how we can handle that without divulging too much state to the hypervisor. Secure nested paging is the next step, and this is where we add integrity protection to our confidential computing model, and we do that through the reverse map table, or the RMP. This gives us a one-to-one mapping between a guest's physical address of a page and the system physical address in the system in general. We maintain metadata information in that RMP table about who owns the page, what size the page is, whether that page is a VM save area page, things like that. So this is the main area that I want to talk about, which is VM privilege levels. It allows you to divide up your guest address space in up to four levels. VMPL 0 is the most privileged level, and so if you have a service running in VMPL 0, you can protect that service from lower VMPLs, lower privileged VMPLs. The VMPL level is contained in the save area, so when a VM run is done, that's how the hardware determines what VM privilege level it's running at. And within each RMP entry that represents a page in system physical memory, we have permissions associated with that, and those permissions are what decide whether or not a particular VMPL level has access to that page, or the type of access it has to that page. So how do we use VMPLs? This is where a secure VM service module comes in. In particular, we've been working closely with the Coconut SVSM project. There are certain services that you can run within that SVSM. to provide that service to the guest without it being in the hypervisor. You know, a typical example is a VTPM. Normally in a hypervisor environment, it's the hypervisor providing the VTPM, and you can't trust that in a confidential computing environment. So you can run this service at that higher VMPL level and allow the guest to make use of that. Another use we are planning on doing is live migration through there to ensure that all the pages that are modified by the guests do get migrated to the destination. And Pankaj will have a talk tomorrow on live migration. So if you're interested in that, that would be a good thing to attend. How we transition between VMPL levels, fairly simple. We have AP requests, AP create requests, or hypercall requests that we use the GHCB for. Once you create that, it will typically just start running at that VMPL level. And when you want to change, this is where the SVSM specification comes in. You set up your register state. You set up the request in a calling area page, and then you ask the hypervisor to now switch to the different VMPL level. At that point, KVM hypervisor loads, saves any information it needs from the previous VMPL level, loads the new VMPL level, issues a VM run, and you're now running in the requested VMPL level. When VMPL 0, in this case, say, wants to transition back to the guest, it's just going to say, okay, now run VMPL 2 in this example. So it's always up to the running guest code to request this switch. KVM will just always perform a VM run with the VMPL level that it needs or is last asked about. I'm going to talk about 3 possible approaches. There are more, and after LPC, there's yet the one that probably is going to be used that isn't listed here. But it's a kind of hybrid of something here. You can have a VM where you have each vCPU in the VM contains all the different VMPL level context. Or we could have a VM where each vCPU is a dedicated VMPL context. Or you could have, and when I say VM, this is a KVM struct, VM struct that's returned back on a create VM call. So you could also have a VM, a guest VM that has 1 VM per VMPL level. The picture that I'll show later will make that a little clearer. So let's get into talking about these different approaches and how we create and transition between them. So in the first approach, you could have 1 VM and each vCPU has all of the VMPL context. Everything stays within KVM at that point. When we go to create the vCPU VMPL level, it's just a request from the guest. We save the information from the guest, kick the target vCPU, and let it validate the input and start running at that point. Execution-wise, if you're running and you want to switch to a different vCPU VMPL level, then it's merely switching fields from the context, particularly the VMSA pointer, which points to, in the VMCB control block, which points to the save area that will have the VMPL level that you're interested in. There's a few other things like the GHCB, some tracking registers that KVM uses that we also would swap. And as soon as the hypervisor does a VM run, you're running in that requested VMPL level. So some of the pros, it's fast, right? We never leave KVM. We switch over to the hypervisor, make some changes, and then issue a VM run. VMM agnostic. VMM doesn't have to know about VMPLs. We'll find later that we are going to need the VMM to know some things if we start putting devices into an SVSM, and we have to possibly do interrupts or IPIs or something into the VMPL 0 level of the like Coconut SVSM. But for now, you know, we don't envision for this approach to require any changes. But we have to save and restore particular fields. And some of the fields are in the VMCB control block that when a guest exits get modified. Some are just pointers to things like the save area or the current GHCB. But that could be a little delicate as far as, you know, newer hardware could introduce something that modifies the VMCB slightly to return some information, and then that's another piece of context we have to save. So it might be a little brittle in that case, right? And then APIC support, as I mentioned, with interrupts, we probably need separate APIC instances. We're going to have different interrupts possibly assigned to different VMPL levels. So that's going to require work on that side to be able to maybe create new APIC instances and associate those. One of the other options is to do a VM, and each vCPU is a dedicated VMPL level. So you would have this logical vCPU 0 that would have under it physical vCPU structures that represent the different VMPL levels. Now we're at this point outside of KVM alone, and so when a request to create a new VMPL level comes in, that's going to have to go up to the VMM. At that point, the VMM will need to start running that VMPL level, new VMPL level, and all the validation and translation will happen on that new run. Kind of same thing for changing VMPL levels. We're going to have to send that request back up to user space, and then user space would have to pause the current vCPU VMPL level and resume or start the target one. So the pros on that, we maintain easily all this context information because it's associated with the vCPU structure. We have separate vCPU structures, so we don't have to worry about have we saved enough information? Are we restoring enough information? We have separate VMCBs, separate VMSA, separate GHCB pointers, everything like that. The cons are that we have to transition to user space. When we start now having multiple vCPUs, it becomes a little more difficult for vCPU pinning. The VMM is going to have to know that if you want to pin vCPU 0 and you have multiple threads for each VMPL, you're going to have to track those and make sure that you pin those appropriately versus just a single thread. Interrupt routing. So there was the patch series from the VSM folks, VTL folks, that introduced namespacing, and you would have to make use of that in QEMU, so we would have to add namespace support into QEMU so that the vCPUs could be easily discerned between APIC ID and VMPL level now. KVM would also require some of that, so interrupt routing becomes a little trickier, and And I think the current version of the patches that I set up that I'll reference later, we basically just say we're not going to inject any interrupts into one particular VMPL level. So it makes it easy, but that would be something that would need to be taken into account. The last approach that I'm going to talk about is having one VM per se per VMPL level, right? And so now we separate out the vCPUs from the other vCPUs. You have to know about the relation of vCPU 0 in one VM to vCPU 0 in the other VM. The request is sent up to the VMM. It creates new CPUs within the new VM that's created. And that new vCPU validates and translates when it runs the information. Similar execution flow though, up to the VMM, it pauses one thread, starts the other thread, right? Similar pros too to the previous method in that all our context information is separate. You know, we don't have to worry about saving and restoring specific data. It's all present. Similar cons, we have to transition to user space. QEMU isn't really set up to understand all this, so it's going to be significant VMM work to do something like this. We'd have to maintain VM to device association so that we can route things properly. And currently with GMEM, we can't share GMEM between multiple KVM structs, you know, KVM VMs. There is work being done by Ackerley at Google to try and change that, but right now it doesn't exist. So for a summary, which approach is best, right? I put out an RFC recently to do the first approach, and Roy Hopkins is somewhere, there he is. He put out an RFC that did a hybrid approach of having separate vCPUs within a single common area within the vCPU, and it's sort of like the second approach. We're currently in the proof of concept only supporting 2 VMPL levels, but we should probably be set up to support more if somebody wants to run more than that. The big thing though is we have to avoid transitions to user space in order for the VMPL switch to be fast. So we need VMPL switches to do validation of memory acceptance. Melody, who is on our team, is going to talk tomorrow about alternate injection, a feature in SNP for secure interrupt delivery. You can imagine if you're dealing with interrupts that VMPL switches could happen quite a bit, so we need to do that very quickly. VTPM, depending on how many measurements are being taken. So I'd like to say that rules out approaches to having to exit to the VMM unless we can figure out KVM optimizations, which, talking at plumbers, we probably have already. So we'll probably talk more on the mailing list about some of this. But it's almost like, I think the concept is almost like a nesting VM, you know, calling create VM within the VM so that we can still maintain context between all the different vCPUs and VMPL levels. So more on that, I guess, out on the mailing list as we, or in a BOF, yeah. So just some references for anybody that wants to take a look at some of this. And that's pretty much it. Any questions?
Just a question. So is VMPL 0 special in some way? Does hardware switch to it automatically sometimes?
It is special in that there are some like instructions that can only be done at VMPL 0. So a p-validate instruction can only be done in VMPL 0. So one of the protocols in the SVSM is for validating memory. So we have to go, if we're running at VMPL 2, we're going to have to go to VMPL 0 to validate memory.
So that's the reason you use VMPL 0 for, and why, any special reason you're using 2 for firmware?
That was just an example.
Okay.
You could use 1, I think initially 1. I think Jorg maybe has a reason why Coconut's using 2. But you could use 3. It all depends on whether or not you're going to have other services that are running at the other levels that you want to be able to protect against.
So there's a lot conceptually here similar to VTLs, and I think it would be unfortunate if we end up with 2 different solutions. Yeah, so
we will not end up with 2 solutions.
Yeah, so with that in mind, I mean, if you look at where VTLs are going towards the per VM, Nicholas, is that still the plan? Yeah, you know, that's really what we need to do for VMPLs, and got to understand how to make those transitions fast or less important.
Right. I looked at the, I don't know if there's been any newer patches, but I looked at the GitHub tree where basically everything was going up to user space to make that transition. And so, yeah, we need to work on a way to not do that and still have.
We need to have basically something that allows for going to user space for a first implementation, but also allows not going to user space if KVM does the work to avoid that. Also because Will correct me if I'm wrong, but I think CCA will not necessarily exit to KVM across exits to different levels, and therefore in that case you just don't have the control. So you need an API that supports all the cases.
Yeah, but I don't think you can have an API that supports exiting from a different vCPU that you entered from, but still compatible with this. I think if TDX and CCA want to do games where the never say never, but no, I think if the trusted module causes an exit on a different vCPU than KVM entered, then it has to be the same vCPU from KVM's perspective, and you just lose the ability to introspect one and not the other.
So same vCPU ID, but not necessarily same vCPU privilege level.
Right, but I'm saying in that case, they need to be the same vCPU logically from KVM's perspective. You don't get separate interrupts. And if you want separate interrupts, give us an API that KVM can actually intercept the transitions.
Yeah, I mean, we need to design that. That needs time. We can discuss it. We will see. I'm not too pessimistic, but of course you may be right.
And I think the other thing with the fast switching would be useful irrespective of confidential computing. I can imagine an oversubscribed scenario where you're running vCPUs on the same CPU, and we already do this to some extent in KVM with the pause loop exiting detection that the vCPU is spinning and yielding to a different vCPU in the same VM to try and release a spin lock. We could do something similar where if user space knows that it wants to run a different vCPU, give it a way to quickly switch without having to exit, in theory.
So it sounds like the way to go here is to switch to your RFC patches to switch to the per VM per VMPL and be slow and go up to user space for now, and then work on optimizations over time to improve the switching.
So first of all, there are, as I'm aware, 4 technologies that we want to support with this level switching approach. That is VSM that AWS is working on. There's VMPLs from AMD. There's TDX partitioning and ARM-CCA. And the last 2 actually support level switches from within the VM, so you can have a privileged level switch without having a VM exit. That's something we need to support, and I think we agree on that. But something we also need is actually separate interrupt sources per level, because the users that we are doing this for, which are non-enlightened operating systems, actually rely on having different interrupt sources or separate interrupt sources per level, and this is something very important to support as well. So
I think this is where we push back on Intel and ARM to fix their implementations. Like to some extent, I mean, TDX partitioning, it's not upstream. We don't even have TDX upstream. Like, if the only concern is that you can see into the guest transitions, that's a ridiculous reason not to exit.
I agree that that's not the reason, but I think if we can make the TDX case close enough to the accelerated case, we might not need that. Like, I'm okay with asking TDX to fix some stuff, but you know how that has gone so far. So I'm more optimistic on being able to do something with a good design in KVM than actually having what we want in TDX or CCA.
It's also not just about the design, but inabilities to do that, right? It's also part of performance penalties. You just pay for these additional round trips. The same way they're trying to avoid user space round trips, the next level up is really just to avoid a low visor exit. We had a small buff last week at LPC where Paolo has interesting ideas on how to actually make that happen, and I think I like them so far. I think they will work. So let's talk about this in the buff. We don't have the 2 minutes left on this talk to go and actually go. Is it 4? Oh, 4 minutes, sure. I don't think 4 is enough.
Let's change the topic of the questions.
And dive into this really deeply, right?
With regards to VMPLs, do you foresee having asynchronous entries into higher privileged VMPLs? No? Like, can't you set up a timer and for the timer to kick in at some point? Yeah. Okay. Okay. So that needs to be supported from day one. Yeah, in API.
Right. All right. Thank you all.
Hello, hello. Right, hello. It's all gone green because it's time for Android. The server stuff was all in black, so we've changed color. Yeah, I'm going to talk today about guest side changes for confidential guests in Android. It's a little bit different to a lot of the stuff we've been talking about so far this morning, because this is obviously not enterprise big systems. I think the Microsoft folks earlier on were talking about this machine with a terabyte of memory. I don't have a terabyte of memory in my phone. And similarly, it's different yet. Yeah, maybe next year. That'll be quite nice. It would make this a lot easier. And then the other sort of difference is we're not really relying on extra hardware support. So this is for things that are out there right now. And that means we don't have things like memory encryption, but that's okay for what we're doing. So just a quick introduction. I think I know a few people here, but I haven't met everybody. I just reused this slide from last time. So yeah, I'm an upstream kernel hacker, co-maintain the ARM64 port with Catalin Marinas. And that's the architecture part, not the KVM part. That's maintained by Oliver and Mark. I'm in the Android systems team at Google. So we're responsible for, amongst other things, the kernel binary that ends up on your phones. And specifically, I work on PKVM, which is the hypervisor that we use in Android. And when I'm not doing that, I'm either brewing beer or catching very large trout. Okay, so a quick recap, because we get everyone on the same page, because this is ARM. The KVM port for ARM v8.0, so that's like the first 64-bit chips. Okay, so it uses this thing called NVHE mode. Now, NVHE mode, if you see on the left-hand side of this diagram, we've got EL0 at the top, that's user space. We've got EL1, that's kernel, and then this EL2, which is a sort of a hypervisor mode, right? And with NVHE, we can't run the whole host kernel down at EL2, because it doesn't give you things you need. It doesn't give you enough page table bases, for example. So what happens is the host kernel, you enter it to EL2, and it quickly gets down to EL1 where it can do useful things, but it leaves behind a stub at EL2. And then later on, when KVM initializes, calls into the stub and basically replaces it with this piece of world switch code. So this is just a giant context switcher, which the host can, when it wants to run a VM or a vCPU, it can call into that context switcher and switch over to the guest on the right-hand side, and that's how it works. So you have a bit of extra latency because you have to bounce through this EL2 all the time, but you'll see why this can be useful in a minute. And when you have this mode, you have this stage 2 translation table, which I think in x86 terminology is the EPT, and we use that for the guest so that you can map physical pages from all over the place to give it this illusion, the virtualization illusion, and similarly, it means that the guest is sort of contained. So this is just normal KVM on NVHE. So with PKVM, we extend that. Okay, so we also now wrap the host in the stage 2 translation, and that's a bit strange. You think, why do you want to put the host in the stage 2 translation? Well, it's an identity map, and we're only using it for permissions. So this means we can do things like unmapping the guest memory from the host, right? Which is kind of similar to what some of these confidential computing technologies are enabling, right? And I've put this silly actual size. This makes the hypervisor look absolutely massive, like 3 kernels worth of stuff. It's tiny. It's like 100 kilobytes. It's just, the diagram makes it look massive. And then in Android, it's the same picture, but all the words change. So instead of task, we have all these Android-y type things, okay? So we have a service on the host called virtualization service. You can talk to that with Java interfaces. Behind the scenes, that's going to go and talk to CrossVM, which is the VMM we're using. Binder is what Android uses for its IPC, for applications to talk to one another. We funnel that across to the guest over VSOC. So we've stabilized the wire protocol for that. So you can call RPCs inside the guest using Binder. We have the Android GKI Linux kernel, that's the binary I mentioned earlier that we ship, that runs on the host. And then in the guest, we build another kernel from the same sources, which we call the microdroid kernel. Now, this is not, you see some folks doing these Linux tinification efforts where they try and get a kernel as small as they possibly can, and they throw out the network stack, and they throw out the console, and they end up with this tiny thing. It's not that. It's more about removing attack surface, enabling hardening options, kicking out drivers for devices we know we're not going to see, that kind of stuff. So it is smaller, but that's not the aim of it really, to be as small as possible. And then it runs a native app. We don't have at the moment any Java support in that guest. And there's this thing here called KVM firmware. So that is I'll talk more about that in a second. that's the first thing that runs in the guest, and that's critical for deriving an identity, a secret identity for the guest. Okay, so let's talk more about that. Today I'm going to focus mainly on pretty much exclusively on the guest side. So what the guest sees, the changes we've had to make in the guest, rather than the host side. There's plenty of really good talks about the host. See Quentin Perez's talk from previous KVM Forum. He does a really good deep dive into the technicalities of that over there. Okay, so when we boot one of these things, we have a few constraints that we need to place on the system. So first of all the secondary CPUs have got to be off, and the hypervisor is going to enforce that. And that's pretty easy to do because we have this specification from ARM that the guest understands and the host understands, and we can the hypervisor knows about that too. So secondary CPUs are off. Okay, and the guest will request them to be powered on when it's ready. So we have a primary vCPU. The set one reg interface is limited. You can set some of the registers. We allow X0 to X14 to be set, for example, in case you want to pass some sort of parameters to the firmware. But the others are reset to poison, or I think probably 0 by the hypervisor. The memory is initialized directly by CrossVM. And as we take guest faults, we transition those pages. We do the normal get user pages thing, right? And as we get those pages, we then donate them to the guest. And so that's going to unmap them from the host stage 2 that I showed you earlier on and map them into the guest stage 2. So CrossVM still initializes everything like normal, but then the pages as they're faulted in become unmapped from the host. And the hypervisor will initialize the PC, the instruction pointer of the primary vCPU, so that we enter via this new firmware blob, this PVM firmware. And then that gets loaded on demand. So the way the host configures where the PVM firmware lives, we've got a new capability. So you can query how big it is, and you can set where you want it to be in the guest space. And if you want to know more about PVM firmware, it's written in Rust, which is quite interesting. It's bare metal ARM64 Rust. It's open source. And I think we've written a bunch of crates as part of that work. So if you're doing bare metal ARM64 Rust, go check it out, because there's things for, creating page tables, driving the GIC. There's VirtIO devices in there. It's quite a good library of stuff. And you can see here in the picture, you've got PVM firmware being loaded by the hypervisor. It validates things like the device tree, verifies the kernel, and then executes it. So I'm not going to talk too much to this slide because I absolutely don't understand all of these details. I'm not a security guy. But you can go and watch this amazing talk from Pierre Clement, who does understand all the details from Embedded Recipes last year. The long and short of it is we have a certificate chain, and PVM firmware is provisioned with a certificate chain from the physical boot of the system, and then it can take measurements of the guest and the environment which it's in, and derive a new certificate which then the guest is given access to. And it then exposes that to user space so you can derive further certificates. And this means that if someone tampers with the guest, he gets a new identity. It doesn't not able to authenticate as it would have been before. All right, so that's the boot environment for the guest. We then have to provide some services, because it's all very well running in a private environment, but if all your memory is secret, fantastic, then you can't talk to anybody, and it's a bit lonely in there. So we've got some hypercalls, and we really mess some of these up in Android. So there's a consistent lesson which you'll see in a minute. I'm not going to upstream the mess ups, but I'd like to upstream something that's compatible so that we can run an upstream guest under Android. It just means there's going to be some funny holes in the hypercall API where we made mistakes. Okay, so there's sort of three families of hypercalls. There's discovery, and then there's some memory sharing stuff, and there's some I/O stuff. So the discovery interface is actually pretty good. We only screwed this up in one way. So this is built on top of all the hypercalls are built on top of this spec from ARM called the SMCCC, which I think is the Secure Monitor Calling Convention or something like that. It doesn't matter. And there's a range. They go, hey, the hypervisor are allowed to use this range, and you have a UID. So KVM has a UID. That's upstream. I think it uses it for the PTP hypercall. Anyway, once you figure out you're on KVM, you can invoke this KVM func features, and that gives you back a great big bitmap of all the hypercalls you've got, so then you know what's available to you. And one of those is the hypermeminfo. So actually, this is quite a good plug. If you're upstreaming this to Linux, write documentation, because this makes it really easy to write slides. You can just dunk it in. So this is the hypemem info stuff out of documentation for KVM, wherever it is. And you can see there's some bits and pieces here. These things need to be 0. If they're not, you get invalid. Otherwise, you find out what we're calling here the memory protection granule, which is fancy speak for stage 2 page size. And you can also check if some of these memory things support ranges. We'll see those in a minute. So we've got that, and then we have another hypercall called func mmio guard info, which also gives you the stage 2 page size. So yeah, we don't need that one upstream. So I haven't upstreamed that, but we have it in Android, and I probably can't ever remove it. It's kind of harmless sitting there, though, as long as it gives the same number. Okay, so moving on, the memory call. So as I said, when memory is initially mapped into a guest, it's donated, which means it's unmapped to the host. The host can't access it anymore. Indeed, if CrossVM tries to access it, it will get a seg fault. So if you want to share memory, for example, to do virt.io, which is the main case that we're using today for this on Android, we've got this share call. So you can invoke KVM funcmem share, and it's pretty straightforward. You pass the IPA, so it's the guest physical address of the memory region that you want to share, the number of granules, so you can support ranges for this call, as you saw on the previous slide. That's detectable from the discovery mechanism. And this is a bit strange. It can return the number of granules that it shared. The idea with this is that we don't want the guest to be able to get the hypervisor to process an astronomically large range, which is doing, in non-preemptible context. So we'll do a little bit, and then we might go back, and you need to resume it. We have an unshare call as well, which it's nice for symmetry, but in practice we never use this. In the future we might, but right now we're just using this stuff to set up SWIO TLB buffers. So that one I don't remember if I upstream that one or not, but it's not needed. And maybe more interesting at the end, there's this relinquish call. So this kind of does the opposite of donating a page to the guest. This gives a page back to the host, but it transfers ownership. So it's different to a share. The page is now unmapped from the guest, mapped back into the host owns it again, and the hypervisor will clear it and perform cache maintenance on it. That is for ballooning. So if you want to reclaim memory from a guest, you have to use that hypercall to drop the hypervisor's reference to the page, but also to make the page accessible so that the host kernel can use it for something else. So you need an enlightened balloon with that last hypercall. Okay, and then the last sort of family of hypercalls is the MMIO one. So by default, if you take an MMIO exit out of one of these protected guests, the VMM can't actually handle it because we don't give it any syndrome information. It doesn't know what happened. It doesn't know the size of the access. We don't give it any ability to update the transfer register, so it can't do the emulation. And similarly, we don't allow it to skip the faulting instruction. There's no mechanism to do that. So even if it could figure it out, it can't actually get off that instruction. And the reason for this is we don't want a situation where, for example, a malicious VMM, because we don't trust the host or anything in this environment, could, I don't know, convince the guest to put its stack somewhere, which is actually MMIO, there's no mem slot, right? And then you could emulate all the accesses to the stack, something horrible like that. So we have this opt-in, so the guest has to issue this MMIO guard hypercalls, and this is one we messed up quite badly, so there's a load of these. So first of all, we had an enroll mechanism, but that doesn't really make sense because when you issue the enroll call, it's kind of too late, right? You could have easily been compromised. If you weren't enrolled already, it's too late. And actually, the hypervisor automatically enrolls the guest, so we don't need that one, so I haven't upstreamed that. We then have map and unmap, but we have two flavors because we forgot to enforce that these things are 0. So that's a good lesson. Everyone knows this, right? You add a new interface, check that unused parameters are 0. You can extend them. And I know that, and people working on this know that, but we just forgot to do it. So we had to add these new ones to support ranges. And the unmap ones aren't really needed either. Like MMIO is MMIO is MMIO. Okay. 10 minutes to go, apparently, so I'll just speed up a little bit, get past some of these. That's not very interesting. Okay. Yeah, I/O bouncing via shared windows. I think most of you probably know this, but we have support for something called restricted DMA. This allows us to instantiate per device SWIO TLB buffers, so there's not necessarily just a global one, and this sort of starts to lead us towards pass-through as well, where we can say we're going to bounce for these devices and not for these ones. This is device tree. We're using device tree here. And yeah, effectively, we just bounce all of our VirtIO data through a per device SPI2B buffer. That's an early con. It's a VT100. This is a bit fiddly. So for the early con to work, we need it to be MMIO guarded before we can probe it. Like Linux prints things very early, and it's before we can do the MMIO guard. So we get the hypervisor to do that. Sorry, the PVM firmware to do that if we are a debuggable VM, which will change the identity of the VM. And you can't use those in production, but it's useful for development. All right, let's see where we are with upstream. Well, actually, we're in a pretty good state. The restricted DMA went up a while ago. I was working with the Chrome OS folks on that. The open dice stuff, we have a miscellaneous device that exposes that CDI chain to user space. And it allows user space to wipe it as well, so you don't leave it hanging around in memory. The hypercore discovery is upstream. The memory sharing just went in this merge window, so we can do the SWI-TOB stuff and actually share the memory back. The GIC ITS, which is our interrupt controller, has some tables that need to be shared, and it doesn't use the DMA API. There are patches on the list for that, undergoing review. I've tested them, they work. So hopefully they'll land soon. MMIO guard, we've hooked into IO remap, so that's upstream as well. And then there's a few optional drivers. So I mentioned the enlightened VirtIO balloon. We haven't posted that, maybe we should. There's a per CPU stall detector we added. That's upstream. And then there's a interesting vCPU freak device for plumbing the guest scheduler into the host uclamp setting. So you can, these things run on batteries, so we have to be careful about perf and power. And yeah, the new code is in this directory. It's very short because it basically just uses hooks in the architecture backend, which have been designed so they can be reused by the ARM CCA stuff. So hopefully we can all share the common infrastructure for this. Okay, I've got a really, really simple demo because I read my abstract when I was writing my slides this week and realized I'd promised a demo. Luckily, Mark kindly brought a device with him, so I've got a Pixel 8 here, and I've managed to flash it with AOSP, and yeah, I can just sort of, I have to do it one-handed because I've got this microphone, but let me just put it down a second and I'll switch to some terminals. Okay, let's see if we can get a root shell. Okay, so this is a Pixel 8. On the right-hand side is an ADB root shell on the device. And you can see, sorry, I'm really bad at typing with one hand. You can see it's a quite old kernel, as you might be used to with Android handsets, but it's a 5.15 base kernel, it's Android 14. And this is unmodified, right? This is a production, all right, it's a user debug build, but it's still an official Android kernel that you would, if you went and bought a Pixel 8, you'd probably have that running on it. Okay, what can I show you in here? I've got a few minutes. So we go into the Apex directory. The place where all the virtualization stuff lives is in android.virt. Okay, you can see here's all the stuff that Android is going to use under the hood for doing virtualization. So for example, you'll recognize in bin, we have a cross VM binary, okay? But we also have this VM binary. And let me make this bigger, there we are. Oops, not list. Oh. So there's a bunch of stuff here, utilities for creating new VMs. I mean, this is not what you would normally use, right? This is for development. So we got the run microdroid where it just gives you a pre-canned microdroid. So let me try and run that. If I get out of this shell, I've got some scripts in here. What are my scripts called? I've got a spawn VM. That sounds helpful, doesn't it? Okay, so spawn VM is going to basically invoke that run microdroid with a -p, which means run it as a protected VM. So hopefully this will work. Spawn VM. Okay, so this is now booting a protected VM, and it's got an empty payload, so it's just sitting there doing nothing now. But if we, maybe I'll make it full screen again. If we scroll up, yep, no problem. You can see here it did some dice derivation. That's using the device, the miscellaneous device I was talking about. And we've got at the top here, so these errors, which you don't need to worry about them, I assure you. These errors are coming from PVM firmware. Which is here. It even says, look, please disregard any previous error. So we don't need to worry about it. It's honest. but yeah, that's PVM firmware which runs first, right? And then the VirtIO console kicks in. VirtIO console kicks in here. So we've missed the first part. So if I go back down and I get out of this, I should now be able to get a CID for that. So it's again, I said all the binder stuff goes over VSOC. So we've got CID 2048. So I can, oops, sorry, one hand. I can get a shell on that VM. 2048. Okay, here we are. So I'm now in the VM. And you can see it's an unmodified middle of the merge window. You can look at that commit. I think it's the LSM merge. So it's from Wednesday when I was at Plumbers. So it's cool. We're running an unmodified upstream kernel as part of our microjig guest. So we've made it. It's great. And that's basically it. I promised a demo. There's not a lot going on. You can see the VirtIO devices. There's the vCPU stall detector. I suppose if we look at the full D message. Oops, sorry. Look at the full D message. You can scroll right back to the top. You can see it probing everything up here. Here's the 611 kernel. Here's the restricted DMA pool, for example. Here are the hypervisor calls. So there's quite a few of them. Even the misfits are here because it's an Android host. And then down in the PCI layer, we start using this bounce buffer. I mean, yeah, it's just kind of, if you didn't have the patches, it wouldn't have done anything. So there we are. It's you can run a mainline kernel on your phone, sort of, and that's basically it. So I think I've got a couple of minutes for questions, if anyone has any. Alex. You can have this one.
So for your VirtIO devices, you've got this bounce buffer.
Yeah.
So you have to copy stuff. You allocate memory and then copy it into the bounce buffer to do the transaction. Is there any possibility of doing the allocation directly in the bounce buffer so you can avoid that copy?
Yeah, that's right. So that's a good question. The V-rings themselves are allocated in there. So if the DMA alloc coherent API, when you're doing an actual allocation, will allocate directly from those bounce buffers. The problem comes when, for example, the network layer gives you an SKB, which it allocated 1 million years ago. So I want you to transfer this, and it's not a page size, it's not aligned and things. You can't just share the whole SKB because there are things like pointers in there, which you don't want the host to be able to manipulate. So in that case, you have to bounce the data through the SWIO TLB. But the ring itself is allocated in there from the beginning.
Thanks.
I assume you've got some sort of, I realize your talk is on the guest side, but I've actually got a host side question, if
All
you
right.
don't mind. I realized that you've, you probably have an IOMMU.
That's
right?
true. Yeah, well, we don't always, but we do have DMA protection hardware. So it can't always translate. But
Okay.
that tends to be okay because we're not doing device pass-through at the moment.
Right, but still, I mean, that IOMMU data page tables needs to be owned by PKVM, right?
Yes,
And
yes.
so when you donate memory, what do you do with the IOMMU to ensure that that remains
right.
confidential?
Yep. That's a good question. So initially we thought, hey, what we're going to do is we're going to force everybody, we're going to assume that everyone has built the latest ARM architecture SMMU, and if they haven't built that, then we won't support it, and we'll have a driver for that. But this is it doesn't really work, right? Because none of the devices have done that yet. So we thought, okay, what can we do? So we have added we've extended the kernel modules, so you can load modules into the hypervisor early during boot. So we have a way that you can load modular code, and unlike a kernel module, you can't just call any code in the hypervisor. There's no export symbol, okay? So when you register, you get when the module initializes, you get a structure function pointers, and you can choose to register. You can say, hey, I'm an IOMMU. I'd like to register myself. And then there are callbacks. So when the host pages change state, we call back into the IOMMU drivers.
And that goes through PKVM?
That's all at EL2, yeah. So,
okay, that's
so
all at
basically
EL2,
the host will, for example, to give a concrete example here, imagine you get a guest exit back to the host, and it says, look, I've taken a page fault. I need you to give me a page. The host is going to go and magic up that page. It's going to issue a donation hypercall to the hypervisor. And at that point, we're going to go and update the CPU page tables, and we're going to call into those IMMU drivers to say, can you make sure that this isn't mapped anymore, please?
Could you tell us a little bit about that enlightened balloon thing?
Yeah, sure. So it's, I mean, we're basically using the balloon driver as is, except okay, if we didn't change the balloon, the guest is going to put the address of the page, the GFN, whatever it is, into the ring, right? CrossVM is going to pick that up. It's going to do the advise. But there are two problems with this. First of all, there is a long-term gut pin on that page because we don't have guest memFD yet. We're doing anonymous memory right now. So there's a long-term gut pin on that page, so the advise isn't going to do anything. And secondly, if it tried to access that page, it would fault. It would be fatal because it doesn't have it back. So the only change we need, and I think we shouldn't upstream this until we figured out the guest memFD story because it's likely going to be different. But the only change we need is to make sure that that guest balloon driver, before putting the GFN in the ring of the balloon, it has to issue a hypercall to say, hey, I don't want this page anymore. You can give it back to the host. Does that make sense?
Jumping back to your IOMMU madness, how do you foresee anything beyond the IOMMU getting shoved into PKVM, into the hypervisor part? And if so, how do you avoid re-implementing module support in a very sketchy ad hoc way?
Yeah, so I mean, you can look at the struct that we currently have for modules, and sadly there is more than just the IMMU hooks. Some of this is a pragmatic decision, so because we want to ship this, right? So this is shipping right now. It's not a made-up thing, right? So we have millions of VMs a day.
More from an
right?
upstream perspective,
Yeah,
because
so
I can't imagine you want to do this.
Yes, you're completely right. So I think for upstream, we might do some of the module support, but I think we would limit it to IMMUs. And there's one good reason for doing that, which is that having a hypervisor where you have, say, 15 different IMMU drivers built in is also bad, because it's a lot of code that's just sitting there. So the module interfaces allows us to get away from that and just load the actual privilege driver for the device we have. I think that's a worthwhile use of that infrastructure.
So when you say only IOMMU code, do you anticipate relying on policy to prevent the PKVM layer from exploding in its TCB, or are you going to technologically enforce that somehow?
Yeah, so we have a point during boot where we prevent, it's quite early during boot, we prevent any modules being loaded after that point. And if you haven't loaded an IMMU, we clear the PVM firmware, so you can't run protected VMs. So we basically trust the host kernel during boot, during early boot.
But how do you trust it to only load IOMMU drivers?
The same way so it's a slightly different for Android. You have to trust the people that make your phone. There are lots of other reasons for that as well.
Okay, you trust the person that built that. Okay.
Yeah, and everything's verified coming off the flash, so it's you haven't run anything else that wasn't verified at that point.
So the short answer is, from an upstream kernel perspective, it's policy to not support arbitrary modules loading the TCB, but technically, from a technical perspective, you could, in theory, if you wanted to do something crazy.
Yes, you could. I mean, so we have debug options where we just don't close the door because it's useful for testing some of this stuff, right? Oliver, and then I think we've got lunch, so make it quick.
Yeah, do you have a use case for actually sharing the GIC ITS tables with the host? Because at least in upstream KVM, the ITS state is just maintained in KVM and not in guest memory.
Are you sure?
Yes.
Because okay, so maybe I'm talking about the wrong thing. But if you don't do this, then the host kernel does like a get user, and it will fault. So.
We use the configuration table from the guests, and that's the important bit. We don't. The KVM doesn't really make the difference between redistributor and ITS. It's one big pile of shit.
and the motivation for that, because like wired interrupts work fine, but MSIs perform so much better because we avoid the IO traps back to the VMM. So,
thank you.
You all look really hungry, so we should go and have some lunch. Thanks very much.
Hello, everyone. My name is Vitaly, and today with me I have Ani, who is also from Red Hat, and we have Alex, who is from AWS. And today we are going to talk about in-guest firmware update mechanism. So we are mostly going to focus on the cloud use case, and by that I mean that the owner of this host and the guest tenant are two different actors, right? So the guest owner cannot change anything on the host owner cannot and doesn't want to change anything inside the guest. Mostly we are looking at getting predictable, meaningful launch measurements for confidential VMs, but in theory this mechanism can be applied to other situations and other use cases. So the question like, why would you want to give the ownership of the firmware, which was traditionally owned by the owner of the host, to the guest, right? And it's quite obvious for confidential VM use case, because for confidential VMs, you are getting launch measurements, which kind of describe the state when your VM was launched. And now you are getting some opaque blob there and some hashes of it, which is like a firmware coming from the host, right? And you don't really know what's inside. It could have been solved by, for example, cloud providers providing reproducible builds of the firmware, but it's not an easy doable thing either. And I will talk why it's not really the full solution a bit later. Also, you may want to do some weird things with your firmware. For example, you want to build SVSM, which is stateful and which does attestation to your own attestation server. You want to hard code addresses, certificates, everything, that you get all these things in your launch measurements, right? And the cloud provider obviously won't give you an option to do that. And once you've done that, you may want to do something while your VM is alive, right? You may want to change this, you may want to fix bugs there, right? So you need an option to update it while your VM is alive. So the question is, why would a host owner be interested in their guest bringing their own firmware? Because it complicates things a bit, right? And again, for CVM use case, it allows the provider of the infrastructure to get rid of this piece of responsibility, which is this blob of firmware inside the guest, which doesn't allow it to say, I have nothing to do with your CVM. Currently, it does if it provides this firmware. Also, a big problem for infrastructure providers is that they cannot really update this blob unnoticed, because it will change guest measurements. Some guests may not launch with these new measurements. And for example, what do you do when you get an embargoed CVE in the firmware, right? And you're a cloud provider. You cannot update it. The guest is going to notice and most likely crash, right? But if you don't update it, then you're kind of responsible if things go sideways, right? And somebody exploits this vulnerability. Yes, the question comes is like, why not just supply, why do we need in-guest mechanism to supply the firmware? Why can't we use something like give away JVM, give it separately through the cloud provider? And the thing is that we cannot have firmware as a part of like guest storage accessible by the host, because in many situations with like real cloud providers, their host cannot access guest storage at all, because the storage comes through like special device which gets it from network something, and it gets like a virtual function and VME function inside your guest, right? So yes, a cloud provider could have solved it by providing a completely separate set of like APIs to manage your firmware, put it somewhere on the side. But again, it's like storing firmware requires storage, managing this. So it's very, very inconvenient for large scale. So now I'm going to hand it to Ani, who is going to describe how are we going to do this.
Thank you, Vitaly. Yeah, so So let's see how we're going to actually solve this problem. So before I go into the details of the various steps that we're proposing, we'll just have a quick overview of all the different stack components that are involved in our solution. And I'll revisit this slide later when I've described the different steps. So obviously there will be changes in QEMU because QEMU needs to interface with the guest, and the guest needs to tell QEMU the blobs, the different blobs that are part of the measurements. And then there is systemd, which is the UKI, that needs to have the support for recognizing the blobs and then loading it into memory. So we'll get to the details later. And of course, also we need to change the firmware, in which case it's EDK2 to actually load kernel and initrd. So let's look at the overall picture of how this mechanism works. So it basically works on a two-stage principle. So first of all, the guest boots with the cloud platform provided firmware. And then the firmware starts UKI. Now, UKI will detect that the measurements don't match because obviously the guest is booted up with a firmware that's provided by the cloud platform provider and is not necessarily something that the guest can trust. So the UKI has is a container format, and obviously it has various sections in it, and it contains the actual blob of the firmware that the end user trusts and is measured. And along with that, it also has the kernel, initrd, command line, etc., all the usual other components that needs to be basically needs to be trusted as a part of the boot process. So the UKI may or may not do signature verification. We'll get to why that is optional a little bit later. The next stage firmware, actually, which is embedded in the UKI, is trusts the kernel image, the initrd, and the command line because the next stage firmware has hashes of this component built into its secure table. So this is exactly the reason why we the signature verification for these components is optional, because when the UKI was built, it was built in such a way that the hashes are known to the next stage firmware for these components. So so that's one thing. And then what happens is that the UKI loads these launch measurements into memory, and it tells the hypervisor where it loaded these launch measurements into memory. So the addresses and the size. And there is also the launch measurements can be mapped privately in the guest memory, or it can be shared. And the UKI also tells the hypervisor whether the particular launch measurements is private to the guest, or it can remain shared. And part of the reason is that when the hypervisor will restart the guest with these launch measurements, it has to make that part of the memory private to the guest. So we need to, so the UKI needs to tell the hypervisor which one is privately mapped and which one is shared. And along with that, it can also tell the hypervisor the target address. So the hypervisor can copy, say, the private launch measurement to that target address in the guest. And along with that, it can also pass the target CPU state data. So when the VM is relaunched, it can launch with those target values for the CPU registers. And so then what the hypervisor does is that it restarts the virtual machine, but it throws away these existing contexts, and it restarts the virtual machine with a new Ceph context. And along the way, it also makes the private memory private. And this time, it is actually running the VM with the firmware that the guest trusts. So since this firmware is trusted by the guest, it also has the hashes for the other boot components, kernel, initrd, etc. So then, after the guest starts booting, when it calculates the measurements this time will be sent over to the external attestation server, and this time it will pass the measurements check because it is running firmware which is trusted by the guest, and that firmware trusts these other next stage boot components like kernel, initrd, etc. So then when the attestation server sees that the measurements are good, it will respond back with keys that will unlock all kinds of secrets within the guest. So then at that point, we are all running in a secured state. And so all is good at this point. So some of this stuff Vitaly has already covered. And so I'm not going to repeat that. And so already I have described some of these steps in details. Yeah, so the other mechanism that we were, one thing is that we're learning as we are implementing this. So we are obviously making some small adjustments and changes. So nothing is written in stone at this point, but one of the proposals is to build a kill switch. So once you relaunch into secured state, then we have a kill switch mechanism where the guest says that this interface can be used only once. So you use it once, you relaunch into a secure state, and then you are locked in. You cannot use the same mechanism to again relaunch into a different secure state. So this is just kind of an additional protection in case there are rogue components within the guest itself that tries to relaunch again with something that's not very trustworthy. So, and let's see what else we have here. Right, so again, so revisiting this, so you can see that we need changes in the QEMU. Now, currently, right now, it is not possible to relaunch or kind of reset a QEMU-based virtual machine when it has already initialized its secure context. So what happens is that once the VM boots up, it's locked in, and the CPUs are not resettable, which means that if you try to reset the guest, it will just terminate. So that needs to be fixed, because now what we're proposing is that the VM, when it resets, it will reset and generate a new secure context, but it will not get killed. So that is something that needs to be implemented, and there's some refactoring work that I'm undertaking, which some of these refactoring is already posted in the mailing list. And then there are some machine changes that are necessary to make sure that the CPU states are, so the VM resets into the target CPU state correctly. So the systemd is mostly the systemd boot, and the UKI changes are necessary there also to be able to parse the firmware config and then provide these addresses and lengths of these blobs and mappings. And also there is EDK2 changes where there is a provision for EDK2 to figure out the platform and capability bits that are exposed by the hypervisor, because what we envision is that when the guest builds a firmware for the virtual machine, the firmware may not be compatible for the underlying hypervisor. And so what the EDK to do would be to check if this firmware is actually compatible. And then if it is not compatible, it will not undergo this process, right? And then, of course, then the loader will load the Linux and initrd into the right locations in memory and then initiate the Linux boot. So I will not go into the details of this hypervisor interface. You can look into the code yourself, which is in the resources section. But before we go there, I will let Alex talk about the demo. And we really are proud of what we can show here. So Alex.
Sure. I figured it's pretty boring to see all of these things without seeing them live. Small caveats on the demo. It does work. It does show you now that we're booting into a new BIOS and a new firmware and into a new kernel. This demo is not running on CephSMP, which is an implementation detail at the end of the day, really, because of the QEMU shortcomings, right? I don't know who actually thought it was a good idea to not implement reset logic in QEMU on CephSMP VMs, but this is the main reason why it's showing you this on non-confidential VMs. The rest of the code would look exactly the same. Second caveat before I go in is the actual ABI is in flux. So if you want to participate in designing that one and figuring out how exactly we simplify that hypervisor to guest interface, be my guest. We can talk after. So what we have is we first need to generate a firmware UKI image. We call that FUKI. It's basically UKI plus firmware that contains all of these components, right? It contains an OVMF binary, kernel, and initrd. And then we need to go and invoke a normal QEMU that loads this particular binary. So if you look at the command line for my QEMU script here, you will see that we have a device firmware update, which is the one that allows us this magic, and that we really just, all we do is we just do an iPXE boot into into our FUKI image. That FUKI image now goes in and loads that new OVMF, and that new OVMF then goes and jumps, basically internally loads that new kernel. So you see this, it comes in. This is the UKI stub, the Linux loader stub, which loads a new debug EDK2. You saw that's scrolling by really fast. I can go back a bit. You saw that somewhere here. So the original EDK2 was a non-debug build. This is a debug build, so you can see it's a very different EDK2, very different firmware that we're running, and that one automatically loads a full Linux environment. A full Linux environment that now is our confidential VM. Interestingly, while I was getting this demo working 2 days ago at in between LPC and KVM Forum, just as a trivia, I was sitting in a park trying to get the demo working so it actually goes and we can show you something. And then this woman comes up and hands me a sheet of paper where she drew me in the park writing, like building the demo for you guys. So here we are. This is back to you.
All right, thanks, Alex. That was quite a sketch. Yeah, so if you want to look at some of the code here, so there is a changes. Again, like Alex said, all of this is a process of evolution. So things are changing, and we're still kind of figuring things out as we go along. So it's all open for suggestions and other proposals of how we want to do this. So yeah, all these people who are involved, thanks Vitaly for basically initiating this project within Red Hat. I got right away excited about this and jumped in. Alex, we had this conversation in FOSDEM earlier this year on this idea, and then so thanks to him for the idea, guidance, demo. Paulo is also excited about it, Yeah, I hope. Yeah. And yeah, so thanks to him for the guidance, and Harald, who did all the UKI stuff for the demo, and thanks to him as well. So thank you very much. If you have any questions, we're all here. Okay.
This may be a dumb question. I'm kind of still trying to get my head around this, but does this only boot Linux guests because you have to do this kind of fancy song and dance? And if it does only boot Linux guests, why don't we get rid of firmware completely, get the hypervisor to load the kernel, an init ramfs image, transition those to private, and then do the attestation on those?
I do not want to revive the Zen kernel init whatever path where you suddenly had to like think of this in a cloud scenario, right? One of the nice things we have with HVMs in cloud scenarios is you have a single reference image. You have one ARMI that contains everything you care about. You don't have random floating around parts that you need to individually update and upload and then go and correlate in any shape and form. With this, you can continue with the current model that we have of booting. Whether this actually does the reboot underneath the hood is a complete implementation detail. Your OS image, the way it runs right now, would also boot into a kernel. And whether it's Linux or not, again, implementation detail. This is all up to you. This is just an EFI binary. You can basically, with this, keep your your current scheme of everything and just move your attestation boundary into your boot phase. Does it explain answer the?
Yeah, it does. I'm just trying to see if you can do that, but with a simpler mechanism of loading init ramfs.
Other vendors do it with other mechanisms. I prefer if we stick to a single boot scheme.
And the other issue is with confidential compute like TDX, you don't have the ability to load in anything except 32-bit unpage protected, so that if you want to jump straight into the kernel, you need some kind of shim to get you there. And obviously you can define AVI so that you can go straight to something, but that get back to then PV. And then you're working with hardware vendors to get them to define the TDX module spec so that it matches your PV spec, and it's just, ugh. So I get why you would do some of this.
So two things. First of all, I think you should build that on IGVM as a standard format to basically pass the state of your to pass your reboot state to the next VM or to the next boot state. I think that would be a perfect fit, because then you can benefit from other tooling around IGVM, like calculating the expected launch measurement and everything.
I can answer that one first. I looked at IGVM. It's a terrible format. Don't use it, especially for this use case, right? It's way too hardware specific. And this particular thing, like the whole interface we have, is like 3 firmware config files that contain a few bits of information. This interface is trivial. You can use IGVM on the other end. Like inside of the guest, if you want to use IGVM to then populate that data to the hypervisor, be my guest. But the actual interface to the hypervisor is way, 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 way smaller than what IGVM gives you, because we're already assuming that most of the data is in memory. It's already well laid out, and you just jump in. Plus, actually the new design, this is as of last week, doesn't transmit any CPU state anymore. We just basically say we allow you to basically override the existingly limited sized BIOS region. Like just basically we give you the right access to the flash ROM for a reset. And then we just use the standard reset vectors. Everything is the same as everything everywhere else. And that simplifies it tremendously everywhere, because you can also reuse EDK2 code, which otherwise explodes.
Yeah, but as you are proposing that this is going to be used at multiple CSPs, you probably want some flexibility and make less assumptions about what is going to be booted. And with IGVM, you actually get that flexibility. You can put in a firmware in the Linux kernel. You can put in a firmware that just boots up. You can put in an SVSM in the firmware. You just get the flexibility with IGVM, right?
I don't believe it's going to be any different with that scheme, but we probably want to look at the actual layout and how this works to conclude.
So just one comment, which actually originates from you, that if you pass an HGVM, right, you will need to receive it on the host side and unpack it, for example, right? You will need memory for that. You may not have it on the host, right? And if the guest puts everything at once in its memory, right, then it just, and now please reboot me. right? You don't need a storage, even memory storage on the host itself, right?
Yeah, so
it may be a problem for some cloud infrastructure.
I may not be up to date with the last developments, but I think it's just a way to do a fancy reboot. Like if you want to support AGVM or even if you want to support Windows, it doesn't really change because if Windows ultimately is an EFI application just like the Linux kernel, right? Okay, then I remembered well then.
Correct, yes.
Okay, just to respond to James, me as a regular user of a confidential compute facility that a cloud service provider provides, I would never want to hand over my kernel and initrd to the cloud provider. So I would never want to do that. No, which is where this is going, but don't give the kernel and the initrd to anyone else, for sure.
Are we at time?
Are we out of time?
Are we or are we not? When is the next one? Oh, 4 minutes. Awesome.
Oh,
next question then.
Reset. You can't really have the host do the reset for you once you're encrypted and all that jazz.
You you destroy all encrypted state, you recreate all encrypted state, and everything that transfers, it has to be shared state. So the old VM, the first VM that boots, the untrusted VM, puts all of its payloads into shared memory because they will be visible to the host anyways, right? They have to be because you're putting them in, including the firmware region. Then you destroy the VM context, you destroy KVM, you create new KVM context, you create a new vCPU, and then you convert the BIOS region, at least in the newest proposal, into private memory, boot in, shared states, shared memory stays exactly where it is. So early boot firmware goes in, reserves these shared regions where it knows that this memory actually resides because it can read them through a firmware config opaque blob that we preserve across that reset, and then it can bootstrap itself.
How do you attest to the firmware that you're loading then? If I understand correctly, you're hoisting it into the VMM through shared memory, and the VMM reflects that back into the new world. How do you attest to that? Because you can't put it into the initial measurement.
You do. Ceph SMP contains everything there is into the in the initial measurement. Okay.
So
is
you'd
your
have to
question
have
is your question around the BIOS blob or about the kernel?
The BIOS blob.
Okay, the BIOS blob is part of your launch digest. You create a new launch digest because you're creating a new VM.
So are you not attesting until the second boot then? You're not.
Correct.
You're never attesting the
Correct.
first boot.
The first boot is
Got it.
untrusted.
Okay.
Plus, I think one piece that we didn't mention, this allows you KExec of confidential VMs.
When you're talking about BIOS blob here, does that include your ACPI tables?
That is up to the guest.
Yeah.
The
Sorry, I guess
guest
what I'm
may
really
or may not want to consult us for their ACPI tables.
What I'm really asking, I think, is does this actually help with the problem of ACPI tables that was raised earlier? How do you attest that in a way that you can reason about?
If you want to build a piece of firmware that embeds the ACPI tables, be my guest.
Yeah.
Like, not you.
It's like for ACPI tables, usually they come from firmware config, but there's two ways. Either you trust that the cloud provider doesn't change them too often and have a contingency for when they change, or otherwise you embed them, cross your the ones that you know about, cross your fingers that they will keep on working even if the cloud provider changes them, but then at least it may fail to work in some cases, but it doesn't fail to attest. You can get them from firmware config, compare. It's a matter of policy in the end.
Correct, and all of that is up to the guest. We are out of the picture, right? We don't mind as the hypervisor. It's guest policy. Cloud Hypervisor, for example, actually allows you to do exactly that. They have a way where you can just say, load this kernel, load this initrd, and load these specific ACPI tables. So all of these are part of your launch measurement. Honestly, I don't think that eventually people will use EDK2 with this. It's going to be a tiny shim that only allows you to run this EFI binary, nothing else, no firmware config access anywhere, and everything you need inside this VM is self-contained. But I don't want to be the one building this. I don't want to have to be the one building it, and I don't want to basically provide this even, because that would put me into the confidentiality path again, right? And that's the whole point why we're doing this. If you don't want me in the confidentiality path, do everything on your own. If you want me, use my hypervisor and trust me when I say it's confidential too. we are out of time, is what the sheet says. So thanks a lot.
Okay, I guess we can start. Hi, I'm Michael Sirkin. I'm the chair of the Virtio OTC. And this talk is about the interaction between Virtio and confidential computing systems. Really, it's mostly call to action. There's been a bunch of work on Virtio in these configurations, and it kind of died down. And what this talk is trying to explain that there's still a lot of things we can improve, and hopefully people will listen to that and want to work on it. So just I'm gonna do a quick background, and then describe like 2 types of configurations that we might want to look at. Then like a bit hand-wavy description of live migration in all these confidential computing configurations. And let's just dive in. Right, so I don't need to repeat yet again. I don't know, maybe I do. There are a bunch of things that confidential computing systems can do for you. And protect again all kinds of attacks to various degrees. Generally not denial of service, because they tend to prevent attacks by denying service to whoever is trying to attack you. And one of the points is that the system, they all use Virtio heavily. One of the reasons is that it's like a defined interface, so it was probably just easier for people to test. So what's the requirement then, right? When we are introducing Virtio into these confidential computing systems, what we want to do, we don't want to, like, because you are using this device, you are trusting the hypervisor more than you did before. With that requirement, right, what we want to do, apparently, whenever we introduce any new feature, we have to consider whether are we trusting hypervisor more because of this or not? This is the way I like to look at it, not at attacks, because not all confidential computing systems protect you against malicious hypervisors, but let's just not introduce new trust boundaries. So, yes. So you can look at Virtio systems, and we can think about 3 kinds, I guess, of Virtio systems, right? And the classical one is all software. So it's just part of the hypervisor from that point of view. Could be, hypervisor could be very complex. Latvia host user, for example, has multiple user space components and the kernel components and so on. But fundamentally, in this case, right, if you are trusting Virtio, then you are trusting hypervisors. You don't want to introduce new trust in the hypervisor, don't trust Virtio at all. And then, well, what if it's not actually a software component? What if we have like hardware, right? So a bunch of people implemented Virtio in hardware, and you would say, well, I trust hardware, right? Because what's pretty common in many confidential computing systems is that people say, well, I have a hardware-based root of trust, right? So I trust hardware. But the issue is that most of these hardware components are actually kind of separate from the CPU that you do trust. They are like across the PCI bus, for example, PCI Express. And so actually, there's nothing that, even though they're kind of separate, the untrusted hypervisor can go and just poke at them. And it can access these hardware systems. So even though it's like hardware, but an untrusted hardware, so it's not even any better. We also have these mixed components, which is kind of from confidential computing. You might think it's like the worst of the both worlds, because we have some control plane, and that's hypervisor. We don't want to trust that. And then we also have this separate component from some unknown vendor that you also kind of have to protect against. So kind of from this, in this classical configuration, standard configuration, what people said, well, then I have to be defensive on the driver side. So whatever driver does, it has to protect the rest of the guest when it's interacting with the hardware from anything bad that this device might do. So the first thing that people did was software IoTLB, right? And that's a very simple idea. So most confidential computing systems protect the guest memory from the hypervisor in some way. So we create this, pool of memory that, yes, it's accessible to the hypervisor, not protected. That's the software IoTLB. And we say whatever Virtio wants to talk to the guest, to the driver, then all the data goes into this software IoTLB buffer. And then the driver will be responsible for copying all the data back and forth, which is kind of nice. And as a nice side effect, it actually kind of fixes the time of check to time of test race conditions, right? Because if memory was accessible in some way, and then the driver maybe can check it, by the time it's trying to use it, it's already different because this malicious device changed it. Here, all the use happens after I copied everything from the public memory to the private one. So that's really good, and it's been around for ages. There is some performance overhead. Most people kind of, at this point, say, OK, I'll pay performance, but I get better security. So, all right. But we actually have to go, and after we copied the data, we have to go and check it. And this is like never-ending grind. We have to go and check whenever we get any patch. It's quite very easy to sneak in some kind of assumption that, yes, the data is valid. We have the specification. It says what it has to be, right? And it's a bit of a difficult mindset to have that, on the one hand, we do expect that if the device doesn't follow the spec, then, of course, things will not work. So yes, it's OK that they don't work. So we have to assume that devices follow spec. On the other hand, we also have to verify that they, and if they don't, we kind of have to fail softly somehow. The approach that was taken to doing that was really fuzzy. So a bunch of hooks were put into the guest kernel, and whenever it received some data from the device, the test will perturb it, and then we just see what happens. And if it crashes, we go and investigate. Maybe that's a hint that something is very bad and not properly validated. And these were the devices that were fuzzes, net, and block and console 9p for some reason, and VSOC. But fuzzing can only get you so far. So one thing that really hard to test with fuzzing is all the Spectre things, the transient execution, right? Because they really don't affect the execution. It's not architectural. So, for example, I can say for sure that right now Virtio has no Spectre barriers in the code at all. And when we use, none of these funky macros that Linux has for safely accessing arrays, we don't have them. Does this mean we don't have any vulnerabilities? Maybe. But that's mostly because the approach taken was fuzzing. It just doesn't detect it. This just before the making this presentation, I went ahead and poked code, and sure enough, I found another one. Another thing that wasn't fuzzed was initialization, just because it's kind of tricky, and most of the fuzzing kind of was just long running VMs. What usually happens during initialization is that you initialize the virtues, you initialize the device, so you normally don't get interrupts until you add a bunch of buffers in the virtues, right? You don't create any work for the device, it doesn't normally do any work. And so in a bunch of cases, we actually deferred a bunch of initialization of the device until after we did that setup. If you don't trust the device, you can start getting interrupts, and boom, here's an example from, I think, a week ago I posted it, that, yeah, actually we previously first we initialized the virtues, and only then we went ahead and initialized a bunch of linked lists. So uninitialized memory access, is this exploitable? I don't know. But it's just another area to just go and look. We had some ideas in trying to address this kind of bug generally in the Virtio core initially. Like we said, maybe we can disable interrupts until all the probe functions are done, but it didn't really work out. Too many devices actually, the probe function tries to go ahead and operate them. So you just, yeah, we have to go and look at that code and fix those bugs. Oh? Okay. So this is just a reminder that, well, yeah, we are talking about Virtio, but just by securing Virtio, of course, you're not yet securing your guest. You have to do a lot of work to like configure. This is most of the guys working on confidential computing seems to be busy, right? They're making sure that the TLS is working correctly with all certificates and stuff in place. You have to encrypt all your storage. Like de-encrypt and DIM integrity seem to be popular, but then you apparently don't have rollback protection. So all of the things kind of still apply on top of Virtio, and that's where most of the focus resides, and it really should, right? Again, I wanted to stress the point that I'm making is not, that if there's like some way to maybe attack Virtio, then everything is worthless, because really confidential computing systems are used in so many scenarios, right? So all of these things are still very valuable. And on the other hand, right, I'm not trying to say we don't need to work on the higher levels, because without them, definitely it's worthless, right? If you don't encrypt your networking, you just do plain text password. So I guess it's not very valuable. So let's just take a look. What else can we do? So if we support blocks, then looks like we also should support SCSI. We have slightly different both performance and feature characteristics, and so we need to do that. Besides that, it's very interesting to me whether there could be use cases for encrypted virtual machines for like desktop scenarios. And like the way I see it, we could see like regulators, for example, come and say like encrypt everything because it's better. And so yeah, then people might say, well, I want that for the desktop as well. And then we will need like input and sound. Hey, there was this presentation, right, about automotive, for example. A lot of users of all of these devices, and people might say, well, yeah, I get extra security. Oh, right. Oh, I have to speed up. Sorry. I'm very curious about VirtuaFS, for example, because like, is there something to be gained from confidential computing if the file system is coming from the untrusted host? I don't know, right? And can we trust with Virtual Crypto to do crypto for us if we don't trust the device? Okay. Maybe I will skip this one because I'm short on time. But really what I was trying to say here in this slide is that if we compare, for example, the security challenge of protecting kernel from the user space and security challenge of protecting the same kernel, right, from untrusted devices, I think the issue is that the interfaces from user space are just much smaller and narrower, right? We just have _ user pointers, and we have copy to user, copy from user, and that's mostly it. We have get user pages, and that's getting messy, but fortunately not commonly used. But with DMA, we have even just for pointers, we have 2 types. We have a ton of APIs like DMA sync. It's just a lot of stuff. Another point is that we have most confidential computing guests apply all kind of filtering, so they want to limit what kind of devices they support. But Virtio has so much flexibility. We also need to develop a way to limit the specific device features that you can use. Otherwise, like for example, I think the version of Virtio that was fast was the version without indirect buffers. So yeah, if either you have to fuzz all features, which is probably not practical, or you have to disable this at the filter level. And we don't have a way to do that right now. Okay, let's try to talk a little bit about TGISP. Because when all this effort about protecting drivers from devices surfaced, like all the Linux maintainers said, well, we are used to be trusting devices, so let's trust devices, bring them into the trusted boundary. That's what TGISP is supposed to do, right? And basically, all the communication between the guest and the device is encrypted then, and it can protect against a bunch of attacks. It has locking. Well, I'm sorry, I'm speeding up a little bit because I'm short on time. So it has locking. So like the hypervisor can initialize the device, and then it locks it down, and that's it. And afterwards, it can no longer modify the device, so that's good. And it has measurement. So after you have locked it, you can check the state of the device, and the guest can verify that it's good. Cool. But it's weirdly limited in that it's been built on top of memory encryption. And so of the 3 types of transactions that PCI supports, which is I/O, configuration, and memory, it only supports memory. And what if your driver is communicating with device using configuration? Then it's not secured, not encrypted, and hypervisor can trap and interfere and do whatever it wants to. And unfortunately, Virtio didn't know about that when it was developed because it predated confidential computing. So it uses configuration, PCI configuration heavily. Like whatever register we want to poke, we have in the configuration somewhere a pointer which tells us which register to poke. Oh, so, and all of this, the hypervisor can intervene and lie to the device. Is all this exploitable? I don't know. Well, we could have the measurement mechanism in place. Maybe we could sneak in all of these pointers that we have in the configuration space inside the measurement, and then have the driver validate it in some way. We'll have to come up with some format to do it. Or maybe the tedious guys will kind of come up with a generic way to do it. Will they do it? I don't know. If we do it, we have to like define a format to do it. It's kind of like yet another transport for Virtaio. So is that worth it? I don't know. I'll skip this one. So instead, if we are doing another transport for Virtaio, we could really do it new transport for Virtaio. That's also an option. It's really not that hard to define new transports. We better, like if we do, and people will try to employ that, we better address a bunch of other use cases which have been asking for new transports for a while, like PCI endpoint, for example. We could somehow make it close to existing one with minor changes, like just move stuff from configuration into device memory. Or we could do something completely different with like DMA. A bunch of people want to avoid using PCI memory. That could be great for them. What unfortunately we didn't think about when we built Virtaio 1.0 is that we might want to do something like this. So if we build it, it will be a challenge. It will be a big challenge to create a device that kind of speaks both languages. People will probably have to decide which one to speak and how far they want to go with compatibility. Let me think what I want to talk about. Let's talk about migration just quickly. So migration, really, you have some state of one device and want to move it to another device and make it behave the same. And if we don't trust the device, then it's easy because even if you have the hypervisor restores the state incorrectly, then, well, it never trusted the device anyway. So worst case, we deny service, and we decided it's okay. But what if we suddenly do want to trust the device? Then maybe we need to define some way that the device will take its state and encrypt it, and maybe sign it, so the hypervisor cannot intervene, and then we move it back to, maybe move it to the destination device. And on the destination side, again, we check the signature and we decrypt. It's probably a lot of work and a bit vague. One other thing, or maybe we can move all of the work that the hypervisor was previously doing into the paravisor. Sounds a bit easier. Let's see. Something similar will have to happen with memory tracking as well, right? If the device is now trusted and it can poke at guest private memory, then we also have to track the changes in a trusted way. We cannot just rely on the hypervisor. Rollback might also be difficult to protect against. What's the best solution? I don't know. All right, that's the summary slide. So for people who are interested in this kind of thing, there's a lot of improvements we can make to improve the security of confidential computing systems by focusing on Virtaio. There is driver work and there is specification work. And we have 2 new mailing lists for the specification work and for the driver work, and I wrote them up incorrectly. It's the other way around. The comment is for spec work, and the dev is for driver devel work. I'll fix it up and upload the corrected one. You have maybe 1 minute for questions? Oh, 5 minutes of questions, right? I completely misunderstood your, sorry. I didn't have to rush so much. All right, thank you very much. Oh, yeah.
For guest to host communication, what are your plans to secure that? Anyways, using Vert.io, anyways, if guest is communicating with host, so that is anyways, if host is not trusted, so anyways,
Yes, then we are you talking about migration or the
not migration in general, because
so yeah, then we have a lot of work because we don't have like a good handle. We have all this mess with all these APIs. Let me find that slide. Just a second. Yeah, like we have a ton of APIs that the guest driver uses to communicate to the device, and we spent a bunch of effort finding bugs in that, and it looks like whenever we add more code, we need to do much more to test it and fuzz it.
okay.
This is less of a question, just more of a comment, just so you're aware. We're working on a new Vert.io transport called Vert.io Message. The use case is mostly for heterogeneous systems where you just have a bit of shared memory and they're not don't share the same interrupt infrastructure.
Mm-hmm.
But also it's built for systems where you have limited visibility, so that only the memory that's needed for the Vert.io transaction is passed to the back end. So I just thought I'd let you know that that's coming.
Oh, that's great. Yeah, maybe that can be reused in some way. All right. Thank you very much.
All right, let's get started. We have 30 slides, so we are short on time. So, welcome everyone to this year's talk about Coconut SVSM here at KVM Forum. We want to talk about progress, plans, and challenges. So, let's just jump in with the progress that we made in the, during the last year. So yeah, a year is a long time. I did not get as far as I hoped to, but we nevertheless made some progress. So we made lots of enhancements towards more idiomatic Rust in the Coconut SVSM code base, which made the code, I think, much more secure. The initial implementation was written mostly by C developers, and yeah, C developers not always know how to write idiomatic Rust, me included. So lots of improvements there. We got a lot of test improvements. So we now have a test runner that actually runs tests in the SVSM context, which is a big improvement because before that we could only run them in Linux user space, which kind of limits the ability of what we can test there. So we have now a test runner that runs in the SVSM context itself. And we also got fuzzers for certain subsystems like the ACPI table parser and the file system, for example, the file system implementation. A big change that we moved towards and which Roy worked on is that we moved to IGVM booting, which is a really great thing because it allows us to be more hypervisor independent. IGVM basically provides the full hypervisor interface that the SVSM needs. So it makes it more independent from that. What progress did we make on platform support? Yeah, the Coconut SVSM was written and is still mainly developed on SCV SNP, which is great, which is a great platform. But of course, Coconut wants to support other platforms as well. So work has started by Intel to port or to make Coconut SVSM run on TDX partitioning. This is ongoing work. There are some challenges there, which I get into later, or which we get into later. TDX support is probably going to look a little bit different because the architecture is a bit different. So TDX does not have a strict need for an SVSM protocol, for example. They can handle everything by just handling the guest OS VE exceptions. And also something that started to appear is support for the native platform, so running in environments that do not have confidential computing hardware protection. Goal here is to make it run in the Hyper-V VSM mode, and KVM is also getting support for this at some point, so it will run there as well. So this is the progress on the platform support that we make. It's, of course, everything is still work in progress, but the work has started on these platforms as well. Another important progress that we made is that we got the TPM emulation code merged. So the SVSM now has a VTPM and is actually useful. So it now actually has something to. It now actually has a service to provide to the Linux OS. You can use it for runtime attestation. It is still an ephemeral TPM, so the EK is regenerated at every boot. So you cannot use it to store your disk key, for example, but you can use it to collect your boot time measurements and use it to basically remote attest yourself to a relying party. So, so this is good progress, but yeah, it's still a big chunk of C code running in SVSM kernel mode, which is something I really hate. But it's like it is, and we are making work on moving that over to user mode, which brings us to the progress we made on user mode support. So actually, most of the pieces are now in place. So we have virtual memory management, RAM file system, and so on. We can switch tasks. We have even user space entry exit code. Elf loader was actually the first thing we had. And yeah, a very simple system code dispatcher. That's one of the things we need to get ready for full user space support. I'm currently working on a user mode support library because that's something we need, like a heap allocator in Rust and a basic library. Long-term or mid-term goal is actually to enable Coconut user space as a Rust target so that we can use standard Rust. Basically, it's a Rust standard library to develop Coconut modules. So there are still some way to get this usable, but I think we are on track for that. So this was a rough overview over the progress that we made in the last year. Now let's get to the plans for the next year and beyond that. I already mentioned the user mode support library with the heap allocator and the system core interface. We have a basic design. Workers has started on implementing that. All of this should lead to, or will lead to, a basic user space infrastructure that we are building up with some kind of inner process that's pure responsibility is to actually launch the other services like VTPM and other services you want to run in the SVSM context, or that the SVSM should provide to the guest OS. Another example is the UEFI variable store that people keep talking about. So so this is the plan for the user space part. Another very important thing that we want to support in the SVSM is having the SVSM support an APIC, or making the SVSM own an APIC, which is currently a bit problematic, but it's an important thing to have before we can actually move on with native platform support and with TDX platform support, because on these platforms we need to have IPI support in the SVSM to do things like remove TLB flushes. So this is something we need to work on, to basically have an IRQ infrastructure and support for an interrupt controller. We'll get there more deeply in the challenges part of the talk. One thing that is probably going to surprise you, but we plan to use the TPR, which Linux does not use, but we plan to use it for certain things on prioritizing IRQs. Another thing which mostly touches the SVSM or the Coconut kernel is to finish the virtual address space split. So currently the SVSM uses a direct map like the Linux kernel does, which is kind of against the goals of the isolation goals of the Coconut SVSM. So we want to finish up the address space split, basically having the address space split up into a global shared part, into a per CPU part, into a per task kernel part, and into a user space part. Each of these parts will get its own heap, and so we can keep everything nicely isolated. We want to move to a page table self map, which is kind of a requirement when you get rid of the direct map. So that's work that has not started yet, but that's on the list of plans. And of course, we want to develop the SVSM, or we want to get the SVSM to a point where it can be a parallelizer for all kinds of operating systems, for unenlightened operating systems, and finally also run, of course, Windows in a confidential VM, where this is where parallelizer support is basically the requirement for that. For those of you that were at Plumbers, you have probably seen the announcement around OpenHCL, which contains all the parallelizer user space support on top of a Linux kernel. Something I really would like to dive into is getting this run in user mode on Coconut. So when they open sources, we will see how difficult it is to make Coconut ready for that. So this was the very rough overview of the plans we have for Coconut in the time to come. Now let's dive into the challenges part. What challenges do we face? The challenges are mostly towards hypervisor support and features we do not yet have in the hypervisors we developed the SVSM for. And since we are here at KVM Forum, I will focus on the KVM part. So the first thing is actually a very small thing, but I don't know how difficult it is to implement. Something I would really like to see, and something we need to run Windows on in a confidential or in an SCV SNP guest is support for VTOM, the virtual top of memory, which basically is a feature of SCV SNP where you can configure a guest physical address, and everything, and the hardware will treat everything below that physical address encrypted and everything above that guest physical address decrypted. that basically turns the C bit we currently have in the SMP page tables into a shared bit, because we can set a specific bit and make an address shared, basically, or have the shared version of that address. What we need for that is basically a way to mirror the PGD entries in the top level page table to above the boundary. So basically, so we can set vterm to a 512 gigabyte boundary with 4-level paging and have basically an unencrypted mirror of guest physical memory above the vterm address. Right. That should actually come before that. So now to the next challenges, and that will be covered by Roy because he is mostly working on that.
Yeah, so continuing on with the challenges, I'm going to start with the synchronization of register state from user space to KVM and through to the VMSA. When you're working with SEVIS and SEV-SMP, the register state is preserved during the guest exits and entries in the VMSA. So the VMSA is encrypted because, of course, that register state may contain sensitive information. But there's actually one instance where that VMSA is not encrypted, and that's when the guest is being launched. And that's because the hypervisor is responsible for populating the initial state of the CPU into the VMSA, which is then applied to that CPU as it started. So if we look at the startup for a SEV-SMP guest, you'll see that all of the pages that are pre-populated into the guest GPA range go through this process of being measured. And so that's via this launch update mechanism in the security processor, which will look at the plain text contents of the page. It will look at the GPA that page is located in, and then it will measure that into a launch digest, and then it will encrypt that page. And when that process is complete, you get to the launch finish, where the launch digest is finalized. Now, the VMSA pages, so this initial configuration of the CPUs, forms part of that measurement, and the location of that GPA, the location of the VMSA and the guest physical address spaces also forms part of that measurement. Which means that if any changes are made to the VMSA, if it's not what's expected, or if it's at a different location, you get a different launch measurement. And then when you do your remote attestation of the report that includes the launch digest, you won't get a match, and you won't be able to verify your guest payload. So the problem that we have is that the initial state of the CPU is set via the IOCTL's KVM set regs, set sregs as well. And then, so KVM builds up a picture of what the CPU is configured to launch as. And then when you get to the KVM SEV-SMP launch finish IOCTL, so when you finish configuring the guest, KVM will take that register state. It will then build its own picture of the VMSA. It will then put that at a specific location in the GPA range, and then it will update that and measure it. But the problem is that not every VMSA entry, not every VMSA field can be set via that mechanism. And also, we've seen, as we've been developing this, there's been changes in the kernel. The floating point registers weren't synchronized at first. SEV features forms part of the VMSA as well. And that has changed based on kernel configuration and kernel versions as well. And it became a problem for us because we've actually got a test. There's a PR waiting to merge in Coconut SVSM that actually will verify the launch measurements. And we can't really get that merged at the moment because the launch measurement doesn't work on every platform. So what we're looking at is a way to directly set the VMSA bypassing the standard way of doing it in KVM. And actually, it's pretty straightforward using the existing IOCTLs. So what I've done, I've put a POC together, which modifies the. Is that on the next one? Yeah. So it modifies the launch update IOCTL to allow it to set a VMSA page. That's nothing controversial, so because the security process is just another page type in there. But it's at the moment, launch update doesn't support VMSA pages. There's a couple of things that we have to do when you do that. The first is that obviously when you're providing a VMSA like that, you have to associate it with a vCPU. So that information has to be passed into that iocta, which it wasn't before. And at the moment, there's an unused flags field, certainly in the version of the kernel I'm looking at. I think it's moved on a little bit since. But I'm using that unused flags field to set that vCPU ID and associate those together. And then when we've actually updated the initial state via this mechanism, we keep track of that via a flag. And you can see it on the right there, there's a VMSA updated equals true. And the reason for that is when we get to the launch finish stage, what normally happens with KVM, as I said, is it will synchronize the state from its register state into a VMSA and it will measure that. We don't want to do it in this case. So it just checks that flag. Has user space already provided a VMSA? Yes, okay, we'll bypass that. So that allows us to actually have full control over the VMSA and also the location of it as well in GPA. Now, this is important when you're using, like, Jörg mentioned, we're using IGVM now. IGVM gives you free flexibility to put whatever you want in that VMSA and locate it wherever you want. So that solves the problem for us. There's a couple of things left to complete. The first is I think I might have to go and revisit, see if we need to add support for SEVES in this. But there's another one, which is that, okay, so we're now setting VMSA state via user space. We ought to synchronize that state back to KVM's initial state, so at least it knows the startup state for the CPU. Once it gets running, all bets are off because, of course, the VMSA is encrypted, but we ought to sync that initial state back again. Okay. So the next one, here we go again, VMPLs in KVM. A lot of talk has happened over the last few days about this. Tom had a great presentation this morning about this, so I'm going to skim over a lot of this, and I haven't got much time anyway. But in Coconut, we need VMPL support, and it's holding us back a little bit that it's not there. So I actually started looking at this from a Coconut SVSM perspective to get something up and running for us, but also to be able to help us to contribute to any upstream work that's going on. So I won't go into what VMPLs are and how they work. I will give a quick example of why we need it in Coconut SVSM. Tom mentioned this morning it's useful for VTPMs. If you have a VTPM implementation running under Coconut SVSM kernel in the guest, it means it's isolated from the host. Fantastic. But without memory isolation from the operating system and the operating system firmware running below that, that could the kernel could go along and scrape the TPM memory. It could reset the PCRs. It could do all sorts of things that basically invalidate the usage of a VTPM. So we need VMPL access to be able to prevent that from happening, to isolate the operating system from the SVSM kernel. So obviously we haven't got upstream support for VMPLs at the moment. Loads of work's already been done on this. Loads of discussions have been going on. We've already talked a lot about this, and the Q&A after Tom's talk sort of showed that. There's a few requirements that we have from a Coconut SVSM perspective. We need something that is going to support multiple architectures. And we don't want this re-implemented every single time. SEV-SMP, TDX, VSM, possibly more than that. But we also need something high performance. So the current sort of work to do the VMPL switches in user mode needs certainly optimization added to it to do that switching inside KVM. And it's worth mentioning again that TDX and others can enter the guest in one privilege level and come out in another. So we need to be able to support that. And at the moment, the one thing we really need to be able to support for Coconut SVSM is an APIC per VMPL to be able to deliver interrupts to any of the VMPLs. So with that, I wanted to get something working that we could run Coconut SVSM on. And so I picked the easiest starting point, which was Tom's patch series, the RFC patch series, because he's already done all of the hard work to manage the switching of VMPLs. And also, storing the state of the different VMPLs when you're doing the switching. What I wanted to do is add at least support for APIC on top of that. I tried two approaches. The one on the left is Tom's first option, if you saw his talk this morning, which was to just create effectively a save area within the CPU to save the state from each VMPL and restore it when you switch. And I won't go into much more detail on that. The one on the right is a little bit more interesting because this is a sort of hybrid approach where you create a a KVM vCPU for every VMPL. So you have multiple KVM vCPUs per virtual CPU, and they're stored in an array, but it's not exposed to user space. So as far as user space is concerned, you still have the one vCPU. KVM is the one that manages the multiple CPUs internally, and this is part of that optimization path. And the way it's done, I'll switch this one to see how it's done. It's easier to see. Is what I've done is an extract. You might not be able to see it, so I'll just describe it. I've created a new structure which manages the overarching state of a vCPU from a VMPL perspective. So it's got an array of 4 KVM vCPUs in there, 1 for each VMPL, and it maintains the current VMPL. And what we do is we add a pointer to that structure, the same pointer to all of the struct KVM vCPUs for a particular vCPU. And I'm using the word vCPU so many times, so this does get a little bit confusing. But basically, we have an array of 4 KVM vCPUs, 1 for each VMPL. And because that's stored as a member inside there, it means that you can easily switch between them. You can have a pointer to the VMPL2 struct KVM vCPU, look at the array inside that, and then actually work out what the relevant structure is for VMPL0 as well. Now, this is a sort of reverse problem to saving the VMPL state, because you have to save the common state. For many of those vCPU pointers, you need to work out what the APIC ID is. You need to be able to hold the mutex on the vCPU itself. So what I've done is I've refactored the common code, and this isn't an exhaustive list, it's just an example, into a substructure inside the vCPU. Now, this is probably the least palatable part about this solution, because what that means is that everywhere that you access that common state over the KVM code, you have to modify it to use the substructure. So yeah, if you look at, I've put an RFC patch series on the list just to show you what it looks like. First patch in that series touches many, many files in many, many locations, although they are trivial changes. But with this, it means that a switch of VMPL level is as simple as just updating the pointer to the vCPU structure that you are using. So when you call the run function, you select the VMPL structure and pass it to the run function. If it changes whilst you're in the run, when you come out the run loop, you say, okay, the VMPL has changed inside the guest, and you can switch which pointer you refer to. So there's some other bits and pieces that you need to do to support this, but actually it's fairly minimal. The creation and destruction logic obviously needs updating. I mentioned APICs. This allows you to have independent APICs per VMPL. We have to choose which one to target when you're delivering interrupts. We're testing this with Coconut SVSM. We're only supporting interrupt delivery into VMPL2 at the moment, so it's hard-coded to go to VMPL2 as per Tom's patches as well. And I've already mentioned about the fact that the guest can switch VMPL, and we handle that on exit. I struggled with this slide. I updated this over the last few days because the what next looked very different until some of the discussions happened over the last week, so I've just left it in an unfinished state. But basically, what next is we need to carry on these discussions about it. I think everyone's a bit more aware about the sort of requirements that are coming up, and we're sort of getting to the point where we could converge on a solution. I believe there's a BOF happening later today. I don't know when or where at the moment, but yeah, that's hopefully some more on this what's next slide is going to be coming out of this. So that, I think, is a good place to stop, and we've got a few minutes for questions, I believe. So, oh, there's lots.
Hey there. So you guys probably talked to some of the ARM folks, maybe even the RISC-V folks, I guess, in Plumbers last few days. So how confident are you in this new hybrid solution that's gonna be compatible with whatever they come with for Realms and RISC-V, whatever? I don't recall what the terminology they use for RISC-V.
So the ARM side is coming up with ARM planes, which kind of looks like TDX partitioning in a way. So for that, I'm pretty confident that it can be easily supported once we can support TDX partitioning. within the code base for RISC-V. I don't know whether they are planning something like that at all. They are planning a confidential computing extension, but I don't know about any plans to support like the privilege level concept. So.
But if we have 3 architectures that are able to do this, this might force them to actually consider that, right? They're still in design phase, so.
Right. Well, one of the main reasons this privilege thing exists is to run Windows, right? And RISC-V does not run on Windows. Windows does not run on RISC-V that way, but they might come up with something like this, and if they do, since CoV also looks pretty much like ARM realms and TDX, it's probably going to be identical. So,
thank you.
Correct me if I'm way off, but this is all about running unmodified guests on Cocoa VMs, right? If that's the point, I'm trying to understand, does it even make sense to run unmodified guests? Surely the guest needs to be able to interact with the Cocoa hardware and reason about the attestation report, and you need all sorts of modifications for it to actually really be useful.
So the full paravisor support is targeting mostly unmodified guests. Even Windows is not completely unmodified. But there's also the use case of an enlightened OS that just needs services in a secure way, like a VTPM. You cannot emulate a VTPM on the host, right, for a confidential VM. And that is also an important use case for privilege levels in these architectures.
How do you API specific VMPLs? How do you select? Do you have a special hypercall and it's through the hypervisor, or?
Yeah, can do. Which in particular was that, sorry?
My question is, how do you select which VMPL you're targeting with an API from a privileged context?
APIs target the same VMPL, do they not?
There's no way of targeting a lower privilege API?
You can do it. It would be possible using this, but I haven't done anything with those at the moment. This is a very quick implementation just to start it off.
So for the load VMSA functionality, one problem that you have is that basically in some cases KVM needs to know exactly what goes in the VMSA, because especially the SAV features, they affect what you are doing. So you also need to validate that you are not putting anything that KVM doesn't know about. And then there are problems because, for example, you may want to put something in there because anyway KVM cannot control your XCR0 and XSS contents. Those are part of the encrypted state. So you may want to put something in there to kind of bootstrap the functionality, but at the same time, you cannot put anything in there because KVM doesn't know what is at that offset. So this is why currently the design is that you cross fingers that the state matches. I think we mostly should have gotten it right with the new API that has VM types for SAVS. If we didn't, that's a problem. I would prefer not to have that, but certainly we can have, for example, the custom GFN if that helps. We need to look at what's missing case by case, essentially.
Okay, yeah, you're right about the validation. So at the moment, we've the QEMU IGVM implementation, which is under review, does VMSA validation, and then the validation is it something we can support to send up to KVM? You know, are there any fields that we cannot synchronize? And I envisage actually moving that, if we go with this solution, moving that into KVM, so it says, is this something we can support? If not, it will fail that update. So we can actually validate that. But yeah,
can we swap that logic? Can we swap the logic and just have a call that says, give me the VMSA? At which point user space can compare?
No, because the VMSA has been pre-prepared by the guest owner and measured as part of the IGVM file, or if you're using IGVM.
Yeah, user space can be the one that fails. So instead of having kernel space do the validation, you can have user space do the validation, and then that and then yes, if it doesn't match, you fail.
No, absolutely, yes, you could do that.
That makes the interface way easier because you don't need to go and put all that validation logic into
Right.
KVM, you just say, give me the current picture that you have of the world that is a VSMA format instead of my other getrecs, and you
Yeah, that's a great idea.
are out of time.
Yeah, we're out of time. No, that is a great idea. Yeah, thank you. All right, thank you, everyone.
Yeah, hello, welcome to our talk. I'm Ollie and there's Stefano with me. Yeah, we're going to talk about Coconut SVSM and early attestation to unlock persistent state. Yeah, so again, super quick intro to what confidential computing with an SVSM looks like. So we have hardware that provides us confidentiality of the guest. So the hardware encrypts the memory and the CPU state, so that the untrusted host and or hypervisor can't access this. Yeah, remote attestation is employed to confirm the initial state of the virtual machine and to know that we're running in the software that we want in the environment that we want. A launch measurement covers the initial state that we then can verify. So the data in use is protected by the hardware, and the data at rest, there the guest operating system has to take care of itself and use disk encryption. Yeah, we have the SVSM, which runs isolated from host and guest in a special privilege level. Yeah, and it can be used yeah, to provide security critical services to the guest, for example, a virtual TPM device. So goals from the end user perspective. So what we want to see is that we want to make it super easy to transition from regular VMs to confidential VMs. So ideally, the guest operating system doesn't need to change much and can mostly stay unmodified. We want to also focus on long-living guests that live for a long time, get restarted, updated, and have a persistent mutable disk. Ideally the guest operating system has very little to do with attestation and other confidential specific things. And we want to support measured boot and secure boot. Because this is what lots of customers expect. How does it look right now? So Linux and OVMF, so the UEFI firmware already work with an SVSM, and Polkadot SVSM provides an ephemeral virtual TPM. Its state is reset on each boot, so it's remanufactured, and that means that its identity changes every time. Its monotonic counters are not preserved, and the non-volatile state is also reset. This is still useful. For example, you can use it for collecting PCR measurements. But what it doesn't work is unsealing secrets with it. For example, you have full disk encryption keys. This doesn't work because this includes the TPM identity, which is not preserved. Another thing is that the UEFI variable store currently is also not preserved, and also starts up empty. So you can't really configure secure boot right now. It's not really possible to implement a secure variable store in this scenario right now because we don't have the secure management mode, which is usually used to protect the variable store. So with this, now we have the questions like how do we boot the guest? How do we unlock the disk? And when and how do we want to do the remote attestation? So if we want to provide a fully functional TPM and preserve all of its state, and if we want to and we also want to provide a functional EFI storage, this could be implemented, for example, by putting a little variable service into the SVSM, which then OVMF can talk to, and then we can manage the access policies there, because OVMF can't do this, as I explained before. So and to make all of this work, in the end, we need to persist the state that, or all the data that the SVSM has, and it needs to be stored across the reboot somehow. So again, so the state is the VTABM state and the UEFI variables and maybe some other things that might come in the future. The idea now is to add a little storage driver to the SVSM, which then can store data on the host provided storage backend. Of course, we need to use an encryption layer because the host can't be trusted. And maybe we even have to implement multiple storage drivers to provide all the different hypervisors that might have different backends there. And now the question is, how do we want to decrypt that SVSM state file on booting? And Stefan.
Okay, so now we have an encrypted state. What we need to do, we need to have a key to decrypt it. So in order to unlock it, the answer is we need to do a remote attestation. I will go pretty fast because we already heard a lot of our remote attestation. So what we need to do an early attestation in SVSM. So we need to generate an evidence from the hardware, send the evidence to a remote server, which is trusted. It works in a trusted environment, and that the server validates the evidence, so check that the software is the expected one, runs on a genuine hardware, and we'll check other parameters. And then when everything is fine, the server will send back to SVSM the key to unlock the state, and SVSM can load the TPM, from the state can load the TPM state, the UEFI variables, the UEFI variables, and so on. Okay, so which are the challenges that we have? First, we don't have, and also we would like not to implement a network stack in SVSM. So since we need to talk with a remote server, we need to find a solution. And then we also want to support multiple attestation protocols. So our idea is to implement a proxy into the host. In this way, we will allow SVSM to talk with the remote attestation server, and essentially the proxy will forward all the requests coming from SVSM to the server using an HTTPS channel. And okay, which are the challenges here? So the application, the proxy that will run into the host will be completely untrusted. So it's a clear man in the middle. So the attestation protocol need to be aware of that. So need to, for example, generate asymmetric key to receive the secret and stuff like that. Also, the host can do some kind of, can change the URL of the remote server, or can change the proxy. But yeah, this for us is kind of denial of service, so it's not really affecting confidentiality. And another challenge is we need to define some kind of protocol, I mean, the channel between SVSM and the proxy. Okay, we did an overview of what we have. Now let's try to put everything together. So the first steps will be SVSM will boots up, as Jörg mentioned. Now we support IGVM, so IGVM will contain the entire initial state with including also the firmware. So we can, in this way, we can easily calculate pre-calculate the launch measurement, hopefully. And at this point, SVSM needs to use the proxy to connect to the remote server. So sends the attestation report, receive back the key, and will be able to unlock the state and load the TPM state from it, and also the UFI variable. Can continue after that. SVSM can continue the boot, launching OVMF, which can launch the OS using the secure boot and the measure boot. Then, since we have the persistent TPM, the OS can unlock, for example, have the key, the root file system key sealed with the TPM, which is a stable identity. And so we can use the standard TPM and to unseal the standard tools to unseal the key and mount the root file system using also the PCRs. We did an intro now. Now let's go a bit deep into details and challenges. One of the last things I mentioned was the communication channel between SVSM and the proxy. So we need a device, of course. Our initial idea is to use a simple serial port. Our proof of concept is doing that, which is pretty easy to support, but for some use cases, maybe it can be slow. So another alternative will be to use a VirtIO VSOC device over MMIO transport. It will be more code in SVSM, but maybe part of it, like the VirtIO MMIO transport, could be shared with the driver for the block device that Oliver will talk later. And our idea is to be not too tied to only on these two devices, but we can be generic to support also either hypervisor specific channel. Then, of course, we need to support the driver in SVSM, and we need to define the communication protocol over this device. Okay, now we need, about the remote attestation protocol, the challenges are, we want to support multiple attestation protocol. This is one example that Tyler is working on. It is the KeyLime-T at boot attestation, but yeah, potentially we would like to support several attestation protocols. Now the question is where to implement the attestation protocol. So the first idea is to, of course, implement it into SVSM. In this way, the proxies could be very, very, very simple. The idea is SVSM will generate the entire HTTP body sent to the proxy, with just forward the request to a remote server. The problem with this implementation could be that every time we need to add a new attestation server, a new attestation protocol, we may need to, or we want to support multiple attestation protocol, we may need to have different binaries with different launch measurements, so it could be a problem. So another idea is to implement the attestation protocol into the host proxy. In this way, the SVSM will be untouched. Of course, we need to define a more sophisticated protocol between the proxy and SVSM to negotiate a lot of things. But in this way, SVSM could be essentially stable, and all the complexity about the attestation protocol will be moved into the proxy. Yeah, another challenge is we talked about stateful TPM. So let's take a look on how the TPM emulation is done now in SVSM. So we have a libmstmp, which is a library that is mainly based on the Microsoft TPM reference implementation, which is written in C. So inside this library, we also have a little serial time library. And of course, OpenSSL, which is the main requirement of the Microsoft TPM implementation. So how to support the SVSM storage API with the Microsoft TPM implementation? One idea, which is one that we implemented in the proof of concept, is to extend the serial time we have in order to support also this libc API used by the simulator into the Microsoft TPM implementation. So fopen, fwrite, fread. So in this way, the idea is to implement that API to use the storage API exposed by SVSM. In this way, we don't need to touch anything inside the Microsoft TPM implementation. And we will use entirely the simulator code, which is there. Another idea, I mean, this is pretty easy to do, but maybe a better idea could be to add a new platform into the Microsoft TPM. So essentially, the code base provides a way to support multiple platforms. One of these platforms is the simulator that we are using now, which is essentially really useful when you want to run on when you have a libc, a standard libc. But what we can do, we have also a lot of examples into the Microsoft TPM implementation, is to add a new platform and base the entire platform on the SVSM API. And for example, we can implement the NV memory read or memory write directly based on that API, and not emulating the libc code. And now back to Oliver.
Yeah, so storing the SVSM state on the untrusted host allows the host to do some nasty things with it. For example, it can attempt a rollback attack, so just feed back an old state file, which the SVSM would be able to decrypt normally and wouldn't detect that it's an old file. That means that, for example, the TPM monotonic counters would be unreliable, and that everything that was saved in it would be gone or would be an old version. This could be one attack. And another thing that they could do is to clone the VM, to spawn a copy of the whole VM with the state file, which would also boot up because everything is exactly as expected. The problem is then we would have the same TPM identity twice or multiple times, which is not what a TPM identity is supposed to be. TPMs are supposed to be unique. To mitigate this, you have to think a little bit what to do. Like an easy idea would be to, against a rollback attack, is to add a boot counter that is kept on the attestation server and also in the state file. And then they have to be in sync and are compared when everything boots up, so that you can't refeed in an old file. And the clone attack is a little bit more involved to mitigate. So you would have to tell the attestation server to only allow one boot at a time. So the user would have to go and prime the attestation server and say now I'm launching the virtual machine, and then the attestation server allows one attestation to go through, so that there are no unauthorized launches of VMs. This would be an idea to stop the cloning. So storage drivers. So how we wanted to add a storage device to SVSM. We investigated two choices so far for which storage interface to use. So QEMU has this pflash interface that is already used by OVMF for the code and for the variables. It's rather simple to implement, but it's also unfortunately quite slow because you have to write individual bytes at a time almost. This could cause some delays if, for example, the VTPM wants to write out its full state at some point. The other option that I looked at is using virt.io block via the MMIO transport, which is, of course, comparatively fast. And if we would implement this, then we would also get other devices almost for free. For example, VSOC. I mean, the most work of this would be to implement the virt queues and the MMIO transport. Of course, this is a much larger code base that we would have to pull into the SVSM. And yeah, we would require some small patch for QEMU to enable the MMIO slot in the Q35 model. Yeah, of course, in the end, it would be nice if we could support multiple different storage backends in SVSM, so to support the needs of different hypervisors. Also, the question was brought up, do we want to maybe agree on one common SVSM storage driver type that then all hypervisors would implement? I don't know if this is useful, but anyway, so there's a draft pull request that I opened that adds virt.io drivers crate from the RCoreOS to SVSM. Yeah, it was not too hard to integrate because the crate doesn't require the standard library, and it just integrated nicely. And it kind of works, but of course this is host-facing code and needs a lot of reviewing and testing. And we also heard earlier about securing the virt.io interface in the context of confidential computing. So yeah, there's some more work to do to make this really secure. Yeah, we prepared a little demo that you can try out interactively. So there's a repository that you can clone, and it includes everything you need to get this running. So this, when you run this demo, you will get the confidential VM that uses the remote attestation via the proxy that was described, and it uses the virt.io drivers to store an encrypted state file. Yeah, and it is able to seal and unseal secrets via the TPM PCR policies. I'm not showing this here because it's not much to see. It's more fun to like try it out yourself. Yeah, so next steps and what's still to do. So on the storage side, we still have to think, do we need a little file system on top of this SVSM state, or is a simple partitioning scheme enough? We need to add more protections. So yeah, integrity protection, we haven't talked about yet, but the host could of course also modify the state file and cause some problems. Yeah, we talked about rollback and clone attacks, which we have to think about. Yeah, we need to decide on which driver to use or which storage backend to use. Yeah, for the remote attestation, it's like, where do we implement the attestation clients in the proxy or in the SVSM? And also we need to decide on communication channels from into the SVSM. Yeah, that's it. And thank you for listening. And now we can answer questions.
Yeah, very interesting. This is more of a thought. I'm not sure it makes sense, but have you thought about opening a proxy through the client, through the hosts? Because in some situations, the host, the hypervisor and the host, and the remote attestation server belong to two different people. The host is on the management network, so you might get to it, but you have to do it in a roundabout way, and that makes network monitoring a bit more difficult because you allow customers to more or less talk to your host, which you normally don't do. Have you thought about doing the proxy through something running on top of the Coconut SVSM, since technically it doesn't need to be trusted?
So what you are saying is that maybe we need to implement the entirely TCP/IP inside SVSM to talk with any kind of network.
No, not SVSM. Something running outside of SVSM. So you're doing the proxy through the host.
Yeah.
And it's not trusted.
Right.
Can you put something that's trusted on top of the SVSM in another VPML, so for example, that can do the connection to the host? It can have the network stack in there. Since it's not trusted, it doesn't really matter.
Yeah, we can do that. The problem is we need to talk with the server as soon as possible to load the state. So to load the TPM state. So we can also do in SVSM implementing a user space stuff, but our main concern is we don't want to bring TCP/IP and stuff like that into. So we always, in that case, we also need to go with a proxy. Otherwise, the other solution is just attack a NIC into the SVSM and then implement the entire stack.
So my idea is to move it completely out of SVSM, put it on, yes, call it a service OS that you don't really trust. And then it will do the connection.
Okay, but which kernel will run there? Is a Linux kernel? What?
Whatever kernel. It can be another VM, just something that does connection. So what I'm trying to avoid is passing through the host, which in some cases might be problematic because it's in a management network and you don't want to allow customers to connect via the management network.
Yeah, I think it's doable. Yeah.
All I'm saying is that another VM is an interesting idea if it is not too complex. Just run the proxy there and then we don't have to build in SVSM. I don't know how difficult it is.
I don't know. It's just I'm just thinking on the fly here.
Yeah.
Was you want to ask a question, Fabiano?
We start to have like a chicken egg problem then, because if you want to have like a trusted internet connection to make sure that your trusted VM is okay, like how do you trust the first trusted VM that you want to start the internet connection in that, right? So that's the part that I guess gets a little bit messed up.
Yeah, but I mean, we are seeing that there is some convergence towards allowing multiple. What we're calling it again? It's not VMPLs any longer, but I mean the more general concept of partitioning, right? I mean even in cases where confidential hardware is not available, so maybe there is a way that we can bundle. I mean a confidential guest with a confidential with a trusted SVSM, but with a non need to be trusted sidecar VM that can take the role of being the proxy, a very simple, stupid VM that is untrusted, that is only can only communicate with the SVSM and vice versa, and the SVSM can make that part of the TCB to make sure that this is the case, but only communicates with this secondary sidecar VM to do the proxy, and then we don't need to do anything about the host. Things like IGVM, right, and partitioning of that needs to be available for us to do that, right?
Can you please go back one slide to the next steps thing? The attestation client in the proxy, I'm not a big fan of that idea. What I would like to treat the hypervisor interface just to be an untrusted communication channel, and everything that we need to trust should be inside the SVSM. I think it's not going to be a big issue because we can implement an attestation protocol as a user space process probably, and it will be bundled up for each hypervisor differently anyway. So each hypervisor can choose which protocol to use. So
do you mean that the channel between proxy and SVSM will be just an HTTP proxy?
Right. So whatever attestation protocol gets implemented, we just rely on an untrusted channel to the proxy, and the proxy is just a dump tool that basically does the VSOC or serial port to network translation, and everything else happens basically inside the SVSM.
Yeah, it was our first idea.
Yeah,
The second is just if we want to avoid to, if we want to make SVSM generic enough to support any kind of proxy without touching SVSM. This was the pro and cons of the two.
Yeah, right. And for the communication channel, I think that can be flexible as well, or it has to be flexible to be cross-hypervisor. I'm fine with choosing a default one per hypervisor, but yeah, it doesn't really matter whether it's serial port or VSOC, or I don't know what Hyper-V provides, but yeah.
In theory, they also have some kind of VSOC.
Yeah, I think it's called VM bus there, but yeah, it's something similar. So
yeah, by the way, I agree. We need to be
Right.
hypervisor agnostic and support several drivers with that, like
Right.
for the storage.
Right, it's the same is true for the storage. We need to be also flexible on that side. My remarks.
Just one comment about the proxy, if I may. We have to make this like in a way that this is like plug and play with any kind of. You guys are started playing with this with Keylime, but I just imagine this like going to the distros with Keylime, and then like someone else wants to add their own, and it just may take like 6 months so they can get this into production, right? So any kind of a plug and play mechanism that can just allow someone to drop something there and be able to use their own, that would be needed.
That was the idea, to move the attestation protocol into the proxy. So in this way, you don't need to touch SVSM at all. You just need to implement whatever you want into the proxy, and that's it.
Klaus.
I just wanted to reinforce maybe the sidecar thing, sidecar VM could be really interesting with the general mechanisms for us having, in the same VM, even for cases where the confidential hardware is not available, scheduling, one particular VMPL 0, VMPL 1 or 3, 1 or 2, and then, we could delegate to that untrusted VM to pretty much do anything they want. Have a freaking network stack, have a proxy, have even be completely controlled by someone else that decides who they need to talk to, because we can guarantee who they are talking to at the SVSM level as part of the TCB.
Yeah.
And then how that message comes across and in what format, in what protocol it comes across, it can be completely untrusted then.
Yeah, it's exactly like the proxy, right?
Yes,
the only
a proxy that is only part
inside
of the single IGVM image.
Yeah, right.
Right. Instead of us actually requiring changes to the hypervisor, to the host.
Yeah, instead of providing just an application, we need to provide like the entire VM to
package
boot somewhere.
Yeah.
Yep.
Yeah. So one challenge with putting the attestation clients in SVSM is that you now get tied to a particular attestation protocol. Today it might be Keylime, tomorrow something else might come up, maybe something using RAT's framework. So maybe the sidecar thing might be the way to go, so that you're not tied to anything in particular. So SVSM becomes neutral. You push everything that is dependent on any particular protocol or communication protocol.
Yeah, it will be, it's exactly the proxy running in a different VM instead of the host. Will be, the proxy will be exactly the same, just what we will change is where it runs.
Yes.
Yep. It's over. Yeah, we are out of time. Thank you.